The topic is sorting technique. There are various sorting techniques. Here I have a list of sorting techniques that I am going to discuss. So many sorting techniques are there. Each has its own method of working. We cannot say one of the sorting technique is a best sorting technique. There is some criteria. Based on that, we compare the sorting techniques, and suitable for your requirement, you can select a particular sorting technique. So what is the criteria for comparing those sorting techniques? So first of all, we should know the criteria of comparison of those sorting techniques. Based on the criteria, we will be studying them and analyzing them. So first of all, let us discuss criteria. See, sorting techniques are analyzed based on number of comparisons. For sorting the elements, a sorting technique may be comparing the elements, and if it is comparing, then total how many comparisons it is performing. So actually total time taken by a sorting technique depends on the number of comparisons only. So this number of comparisons decides the time complexity of any sorting technique. Then the second one is how many swaps. See, for arranging them in the order, increasing or decreasing order, the numbers has to change their places. So it has to swap the elements. So swapping is a common process done in almost all the sorting techniques. So how many swaps it is performing? We will analyze how many swaps a sorting techniques is performing. Then third one is adaptive. See, when you are trying to keep the elements in the sorted order, what happens if they are already in the sorted order? Already they are in increasing order and I am trying to arrange them again in increasing order. So if they are already in increasing order, then the sorting method must take minimum time or a less amount of time, because it doesn't have to rearrange the elements. So if any sorting method is taking less time or minimum time over already sorted list, then we call that algorithm as adaptive. So sorting procedure or algorithm, we call it as adaptive algorithm. Then this I have to explain you using an example. What does it mean by stable? So I will finish this. Extra memory. Out of these sorting algorithms, there are some sorting algorithms which requires extra memory space for sorting the elements. Apart from the space consumed by the element, they need extra spaces. So not all, few require that. So we will analyze for every algorithm whether it requires extra space or not. Then I have to explain you stable. So I'll remove this and take an example to show you what is the meaning of stable and importance of stable. Now let me explain you what does it mean by stable. For explanation, I have list of names and marks. Actually, these are records of students. Suppose these are student names. I have taken just alphabets, names of the student and their marks. Right? Now this list is already sorted based on names. Now I want to sort based on marks. So if you look into the marks, two students are having same marks. First is C, then next is E. So there are duplicate elements. When I sort this based on marks, what I want is their order should not change. That this 6 should come first, then this 6. What is the difference? Both are 6 only, na? No, that is the reason I have kept other values also here. This 6 belongs to C, this 6 belongs to E. So that C should come first, then comes E. The order should be preserved. If a sorting algorithm is preserving the order of duplicate elements in the sorted list, then that algorithm is called as stable. Let me sort this and show you. Lowest marks, the smallest marks are 4. So D 4. The next is A 5. The next is 6. So which is 6 I should take first? This one only. So if I am getting C6 then E6, then we say that the sorting procedure is stable. If any of the sort is preserving their order as it is, then we call that sorting procedure as stable sorting or stable algorithm for sorting. I'll finish this, I'll write the rest of the numbers also. So stable means if there are any duplicate elements in the original list, then in the sorted list, their order must be preserved. Now next question, why? Why we need this? Reason, listen. See, already this list was sorted based on names. Now I am sorting them based on marks. If I sort them based on marks, it will not be sorted upon names. No more, definitely. See, the names are different, D, A, so they have changed their order. But if there are duplicate marks, then at least their names must be in the sorted order. First C, then E. This is the requirement. If you are sorting a record upon multiple columns, name, then roll number, then marks, like this, if you are sorting them, then this is the requirement. First sorting was this one. Now when we sort upon marks, that is lost, but it will be preserved if duplicates are there. So this is commonly used in databases. So we want a sorting algorithm in database such that if you are sorting upon multiple columns, then it should preserve the result of first sort in the second sort. Means if there are duplicates, then their order should be preserved. This is the requirement. So not all algorithms are stable, few are stable, I will show them. So that's all, we have finished with the criteria for analyzing sorting algorithms. Now I'll briefly give you the idea about all these sortings. I have listed them, then briefly I will talk about them. We are going to learn about all these sortings one by one, but just let us get a broader picture of all these together. See, all these sorting algorithms from 1 to 8, these are called as comparison based sorts. All these are comparison based sorts. They sort the elements by comparing with other elements. So one element is compared with other elements and their arrangement is done. Then what about these sorts? These three sorts are called as index based sorts. So these are index based and these are comparison based. Next, these sortings, these three sortings, they all take n square time. So we commonly say n square sorting algorithm, means we are referring to those three. They all take n square. We will analyze this one. When we study, we will analyze this. Just I am giving the overview about this. Then these algorithms takes n log n time. N log n sorting means any of these. Heap sort, merge sort, quick sort, tree sort. N log n sorting means any of these. N square sorting means any one of those. Now these sortings are, so these are order of n or multiple of n, but they consume a lot of space. So they are faster, but space consumption is more. This sorting is n power 3 by 2. So it is faster than this one, but slower than n log n. Shell sort, it's 3 by 2, 1.5, n power 1.5. Anyway, adopt which one is adaptive, which one is stable, I am going to explain it along with the algorithm. When I discuss it, I'll analyze it thoroughly. Just I wanted to show you that some are comparison based sorts and some are index based and some are n square and some are n log n. This categorization you must be familiar with. So that's all. We will be starting from bubble sort. The topic is bubble sort. So in this video we will learn about bubble sort. I'll show you how it works upon this list of elements. Then also I will analyze. Let us see it's working. I have a list of elements, array of elements, 5 elements are there in an array. Now to understand how it works, I will draw this array vertically. So I will take these elements vertically. Indices are 0, 1, 2, 3, 4. I don't need indices. Without indices we'll work on it. So let us start. See, it will compare a consecutive pair of elements every time. If the first element is greater than the second element, then it will interchange the element. So it will compare these two elements. 8 is greater than 5. So 5 will move up, 8 will come down. The remaining elements as it is. So this was the first comparison and the first element was found greater, so it has interchanged. Continue. Second comparison. 8 and 7. 8 is greater than 7. So 5, 7 comes up, 8 moves down, 3, 2. Then third comparison with the next element. So these are consecutive elements, so it will compare them. 5, 7, 3, 8, 2 because 8 was greater. Then compare these two. 5, 7, 3, 2, 8. So I have compared all the pair of elements. Total 5 elements are there and 4 possible pairs are there. So we have compared all possible pairs of elements, right? So when all elements are compared once, then this is called as pass. Pass means we are going through the list. So this is the first time we are going through, so this is first pass. What is the result of the first pass? One element is sorted. Which element is sorted? Largest element is sorted. Heaviest element is sorted. That 8 is sorted in the list. So we have done 1, 2, 3, 4 comparisons. So we have performed 4 comparisons. So there are 5 elements, so we have performed 4 comparisons. That is, if there are n elements, then we have performed n minus 1 comparison. Then how many times swaps are done? Every comparison swap was done. 1, 2, 3, 4. This is the final result. So 4 swaps are also done. Now all elements are not sorted, just one element is sorted, that is 8. Then I have to continue and perform second pass. So I will take this list of elements once again. I will perform second pass. First compare these two elements. See, first one is not greater than the second one, so they are not swapped. They remain as it is. So if it is greater, we will swap. Then next pair, 7 and 3. 7 is greater. So 5, 3, 7, 2, 8. Then 7 with 2. 5, 3 as it is. As 7 is greater, so swap it. 2, 7 and 8. Then 7 and 8, if I compare also, no use because 8 is already sorted. I can avoid that comparison. So total 2 elements are sorted now, 7 and 8. 2 largest element I got. How many comparisons I have performed? 3 comparisons I have performed. Then how many swaps are done? Just 2 swap. Only 2 swaps are performed because here the number was smaller than 7. So at most how many swaps are possible? 3 swaps are possible. So I will write down 3 swaps. This is the maximum number of swaps, not the actual swaps that has happened there. Maximum swaps I am writing here. Now this was the second pass. 2 passes are completed. How many elements we got sorted? 2 elements got sorted. 8 and now 7 also. 7 and 8 are sorted. Now I will take the elements once again, continue this list and perform one more pass. 5, 3, 2, 7 and 8. Compare these two. 5 is greater. So 3 goes up, 5 comes down, 2 and 7 and 8. Then compare 5 with 2. So 5 is greater. So 2 and 5, 7 and 8. That's all. Stop. Because if you compare 5 with the 7 or 5 with 8 also, no use. They remain as it is. Now 3 elements are sorted. How many comparisons? 2 comparisons. How many swaps? Maximum 2 swaps. Yes. This was a third pass. I will perform one more pass. 3, 2, 5, 7, 8. Compare these two. 3 is greater. So 2, 3, 5, 7, 8. That's it. Comparing 3 with 5 is of no use because already sorted. So I'm not comparing with those elements which are already sorted. So right now, how many elements are sorted? I have sorted 1, 2, 3, 4 elements. But there is only one element left, so that is also sorted. So this whole list is sorted. How many comparisons we perform? Only one comparison. How many swaps are done? One swap is done. That's all. The list is sorted. So this is the working of bubble sort using 5 elements I have explained you. Let us analyze this one and study each and everything of this one. First of all, how many number of passes I have performed? Total 4 passes. 1, 2, 3, 4. I have performed 4 passes. If I separate them like this, you can see them clearly. I have performed total 4 passes. Then how many elements I have? I did not write that. I have 5 elements. So n is 5. See, actually when we are doing analysis, we should do it for n elements. N means whatever the number of elements may be. In our example, we have only 5 elements. So for 5 elements, 4 passes are there. Then for n elements, how many passes will be there? N minus 1 passes will be there. So this is n minus 1 passes. Yes, this is perfect. Then let us find out number of comparisons. See, if I start from here 4, 3, 2, 1. If I count from that side 1, 2, 3, 4. So total comparisons are 1 here, then plus 2, then plus 3, then plus 4. 1 plus 2 plus 3 plus 4. Then for n elements, how many? 1 plus 2 plus 3 plus goes on to, see, for 5 it was up to 4. So for n it will be n minus 1. This is sum of first n natural numbers up to n minus 1. So this is n into n minus 1 by 2. So this is order of n square. See, this I got a formula. Formula is polynomial. What is the degree of a polynomial? N square. So I wrote it as order of n square. Then next is number of swaps. How many swaps are performed? See, actually this is maximum number of swaps, right? Here you can observe that there were only 2 swaps, but I wrote 3. So 3 were possible. So I am writing maximum number of swaps. So maximum how many swaps are there? Again from there, if I count 1 plus 2 plus 3 plus 4. So 1 plus 2 plus 3 plus 4. For n elements, 1 plus 2 plus 3 plus goes on to n minus 1. Then this is also n into n minus 1 by 2. So this is also order of n square. See, number of comparisons are also n square. Number of swaps are also n square. See, from the criteria, I have checked 2 things. How many comparisons, how many swaps. And the time complexity of any sorting algorithm is given based on number of comparisons. So the time taken by this algorithm is n square. Now, out of 5 criteria that we have seen in our first video of this section, I have completed 2 criteria, comparisons and swaps. Remaining 3 are there, whether it is adaptive or not, whether it is stable or not, whether it is taking extra memory. These things we have to discuss. So before going to that analysis, let me discuss few interesting things about bubble sort. See, first one, why it is called as bubble sort. See, this was the list of elements. This was the list, right? This one. 8 is heaviest element. So if you drop it from here, it is going down and settling at the bottom. And the other elements like 2, 3, 7, 5, they are lighter elements. So they are slowly moving up. So they are moving up. So the effect is just like if you throw a stone in water, then stone is heavier, so it will go and settle at the bed. Then the bubbles which are lighter will come up. So that's why the name of this sort is bubble sort. The effect is just like bubbles in water when a heavy thing is thrown in water. I don't know who observed this and given the name, but this is what the observation based on which the name bubble sort is given. This is the name. One more interesting thing. In one pass, I got the largest element. Then second pass, I got 2 largest element. Third pass, 3 largest element. For some n elements, if I perform k passes, then what I get? K largest elements I get. K largest element. Suppose you have a list and you don't want to sort everything, just you want which is greatest. Just perform one pass. I want first 3 greatest number. Perform 3 passes and stop. So you can take the help of this procedure, this algorithm, for performing selected number of passes to get desired result or required result. Now I will remove these things, then I will just write on a piece of code showing bubble sort, working of bubble sort. I'll remove this and show you. I have a function for bubble sort. So what is the work we are doing in this one? We are performing n-1 passes. So we have to repeat something that is passes for n-1 time. So I will write on for loop directly. This for loop is for passes. For I assign 0, I less than n-1. If there are n elements, then n-1 passes we have to perform. So this will be repeating for n-1 time. Then in each pass what I have to do? I have to compare this element with the next element. So if I say this is j, then compare it with j plus 1. Then again bring j here and j plus 1. Then bring j here, then j plus 1. So I need one more loop for comparing all the elements, consecutive pair of elements every time. So I will take one more for loop for j. Now for j assign 0, j less than n minus 1, j plus plus. So this j will be moving along these elements. Here also I wrote n minus 1 because if there are 5 elements, then I should perform only 4 comparisons. Yes, correct. But one more thing, in the next pass, one comparison should reduce. Then again next pass, one comparison should reduce. So in every pass, one comparison should reduce. So not just n minus 1, minus I also. So it means first time in first pass, I is 0, so nothing is subtracted. Next pass, I will be 1, so 1 will be subtracted. So this becomes n minus 2. So j minus n minus 1 minus I. Why I? Because in every pass, one comparison should reduce. Next, what I should do inside this loop? I should compare a of j with a of j plus 1. If a of j is greater, then swap. So here check if. So I have written the statement. If a of j is greater than a of j plus 1, then swap them. Swap means 3 statements I have to write on. Instead of writing 3 statements, I just wrote swap. So swap the elements a of j with a of j plus 1. That's it. So logic is very simple for bubble sort. And you can see that there are 2 nested for loops. For loop is there, then inside that one more for loop is there. So from the code, if you see, if you have 2 for loops that are nested, then the time is n square. And both are working based on n only. N. So time is order of n square. From the code also you can see this one. Next. So I have written the code. Now next thing, let us understand whether it is adaptive or not. So for that, I will take a list which is already sorted. See, this list is already sorted. Right? Let us perform bubble sort on this one. And we will perform first pass. First pass. So in first pass, compare these 2 elements. Swapping is required? No, this is not greater. So write the elements as it is. Next, compare these 2 elements. Is it greater than this one? No. So write down the elements as it is. Can you tell me this comparison and swapping, where it is happening, in the outer for loop or inner for loop? Yes, it is happening inside inner for loop. This is j. See, this was j was here, right? So j plus 1. Next time j was here, j then j plus 1. So this is happening inside this loop, inner for loop. And this condition is not true. This condition has failed. First time also the condition was false. Second time also condition is false. Then again check next. So j should come on this one, right? So j should come on this one. Compare these 2. So these 2 are compared, j with j plus 1. J with j plus 1. Is it greater? No. So swapping will not happen. So elements are as it is. The next j is here on this one, right? Compare these 2. Then is it greater than this one? Is it greater than that one? No. So it will not swap. So the elements are as it is. So we have completed one pass, and in this entire pass there was no swapping done at all. So it means inside this for loop swap was never done. Swap was not done at all. No swap was done. If no swapping is done, means we can say that the elements were already sorted. That is the reason swapping is not done. Yes. Yes. We can identify that if the list is already sorted or not. If there is no swapping, then the list is already sorted. So for that, I will take one variable called flag. This flag variable, I will initialize it to 0 before entering into a pass. This loop is performing pass, right? This is for repeating the passes. This loop is for comparison. See, just now we have done all these. So this is happening in this one. So before starting this, make flag as 0. And if any swap is happening, make flag as 1. Means there is some swapping done. Then outside this for loop, there is no space here. So I will write down here. Outside this for loop, check if a flag is still 0, means swapping was never done. We can identify like this. So here I will write down, if flag is still 0, then break or stop or return, whatever you want, you can do it. Then closing of outer for loop, then closing of function. So I can use one flag variable and make the flag as 0. before every pass, and inside this for loop, if swapping is done, then I will make flag as 1. Outside this for loop, outside this inner for loop, once the pass has finished, check if a flag is still 0, means swapping was not done, and break. Break means it will come out of this outer loop also and function stops. Or else you can say simply return. So by introducing a flag, we can identify whether there was any swapping in a pass or not. If no swapping means list is already sorted. So this may happen in first pass or second pass. In any pass it may happen. Whenever it is happening, it will stop. If the list is already sorted, then it will stop after first pass only. Now analysis. What is the time taken if the list is already sorted? It is performing just one pass and it will break. So in one pass, how many comparison on how many swaps? Number of comparisons are n-1. Swaps 0. So it's not performing any swap, 0 swaps. So n-1 comparison means the time is how much? Order of n. So we can now say that bubble sort time, minimum time taken by bubble sort is order of n, maximum time taken by bubble sort is order of n square. This n square already we have seen. Then n is now we are looking at. It is taking order of n when? If the list is already sorted. So bubble sort is having minimum time also, maximum time also. So if the list is already sorted, then it is taking minimum time. So bubble sort is adaptive. Yes, bubble sort is adaptive. So this is adaptive. Yes, true. So by itself it was adaptive, or we made it by using flag. We made it by using flag. So we can make bubble sort as adaptive. By default it is, by nature it is not adaptive. We made it. So it is possible to make bubble sort as adaptive, and the bubble sort is known as adaptive algorithm. Then one last thing, whether it is stable or not. To study whether it is stable or not, I have taken a list of elements. Let us see the list. See, there are duplicate elements. So let us start bubble sort on this one. So first pass, first it will compare the elements, this element. If first is greater than second one, then interchange. But first one is not greater than second one. It will not interchange. So I will do one thing. I will write this 8 with red color so that you can identify. So will it interchange? It will not interchange. That black 8 remains as it is. Then red 8. Then 3, 5, 4. Then it will compare these two. Then this 8 goes down. So 8, 3, 8, 5, 4. Yes. So that was first 8 remains there only, right? The second 8 will come at the bottom. Then above that, that first 8 will come. So their order is not changing. It's not switching the elements like this red 8 is coming first, then this black 8. They are not changing the order. This will not happen. Because if this is greater, then only it will interchange. So bubble sort will interchange only if the first element is greater than the second element. So that's how bubble sort is stable also. So yes, it is stable. So bubble sort is adaptive, bubble sort is stable. That's all about bubble sort. In this video, we look at a program for bubble sort, and we have to see more sorting techniques, and all those sorts I will write down in a single program. So I'll be using the same project for showing you all the sorting methods. So let us start with bubble sort. So I will give the project name as sorts, and this is using C language. Here inside the main function, I will declare an array having few elements. So I will write on random few elements. So here I have taken 10 elements. So also I will have one variable n whose value is 10. So that's it, I am having 10 elements. Now let us write a function for performing bubble sort. Function name is bubble. It takes a integer type array and also its size. Now already we have discussed the logics. The same thing I will have to write down here. I will take some temporary variables like I and j, which I'll be using it for loops. So the procedure is for I assign 0, I is less than n minus 1. I plus plus. Then for loop, j should start from 0 and j should stop at n minus I minus 1, that is, it should stop one element less always. So it should go on reducing, then j plus plus. Then inside this, I should check the condition if a of j is greater than a of j plus 1. If so, then I should swap the elements. So for swapping, swap is a common function. So for that, I will write on a function just above this bubble sort. So I will directly use it here. Swap address of a of j with address of a of j plus 1. That's it. There's a bubble sort function. Next, okay. Then that's the end of for loop. That's it. This is the end of bubble sort function. Then I will write on swap function above this bubble sort function. That's all in bubble sort, and here I will write on one function called swap. So swap function which take two pointers like say x and integer y, addresses of two values. Then here in temp it should assign value of x, and the value of x should be changed to value of y, and value of y should be assigned with the temp. That's all. This is a swap function. And bubble sort is a very small function. It's completed. Now inside the main function, I will call bubble sort. I will pass an array and the number of elements are 10. After this, I will display an array. So for that, I will take a for loop for I assign 0, I is less than 10, I plus plus, printf, printing an element, percentile d, a of I. So this will be displaying all the elements. After that, I will give a new line to get a proper output. Yes. Now for this, I should also declare one more variable. After n, I will declare one more variable I. Let us run the program and see. Yes, it has sorted all the elements, that is 2, 3, 4, 5, 7, 6, 7, 9, 10, 11, 12. I got all the elements in the sorted order. That's all in the bubble sort. We have already seen that we can improve bubble sort and we can make it adaptive by introducing a flag. So let us introduce a flag inside bubble sort. So here I and j already we have, so I will take one more variable flag, that is flag is initially 0. And before the start of every pass, I will make flag as 0. And inside this, whenever it is swapping, I will make the flag as 1, means there is a flag, there is a swap flag as 1. So as many times it is done, it will become 1 only. So at least one time if it is done, then flag becomes 1. Then after the first for loop, that is after a pass, I should check that if flag is still 0, it means there was no swapping done, so it means the array is already sorted. So break. So that's all. This is the improvement in bubble sort. So now it has become adaptive. So I will change the numbers and see how the bubble sort works. Now upon these numbers, let us run bubble sort. So I will not take so many numbers. I will reduce the size now. I will take only 4 numbers and n size is also 4. Now let us run bubble sort on this and see how it is working. Then we will give the elements in the... So now let us run bubble sort and see these are all sorted elements, how bubble sort is working. I'll put a breakpoint on bubble sort and now run. Now it will enter into bubble sort. Yes. Now you can see that the elements are already sorted, that is 3, 7, 9, 10, and there are 4 elements here inside the debug area. If you see, if I press F7 and go line by line, now it is entering into the first for loop, then flag is 0, then it has came out of the first inner for loop. Condition is false. Okay, condition is false. Then next time also condition is false, flag is still 0, break. It has came out. So it has performed only one pass, it has gone through all the elements only once. So that's all about bubble sort. We have improved it also and made it adaptive. So you can practice this program. That's all in this video. The topic is insertion sort. This is one of the important sorting technique. For understanding insertion sort, we must understand why the name insert is taken. So insertion means what? If we understand that, then the sorting becomes very easy, and the same idea is followed by insertion sort algorithm. So let us understand what does it mean by insertion here. So for understanding insertion, I have taken an array, a list of elements, and these elements are already sorted. And in this list, I want to insert 12 in a sorted position. So it should be inserted at a place where it should come in the sorted order. So here insertion means inserting an element in a sorted array at a sorted position. So it should be inserted at sorted position. Let us see how we can insert this element in a sorted position in an array. Now listen carefully. Where this 12 should come? So after 2, after 6, after 10, before 15. It should come here. 12 should come here. Then insert 12 here. For inserting 12 here, what I have to do? I have to shift all these elements on the right hand side. Make a free space here, then insert 12. So if you observe what I have done, I first found out where 12 should come. Then I said I'll be shifting the elements. So the important thing is you don't have to find out where it should come. Directly you can start shifting the elements. You don't have to find its position. Now I will show you exact procedure how this insertion should work. Let us start. I want to insert 12. The last element is at this index. I don't have indices. Okay, I will write down indices. Last element is at index 6. So is it greater than 12? Yes, shift it. Move to the next element. 25 is greater than 12. Shift it. And next element, 20 is greater than 12. Shift it. Next element, 15 is greater than 12. Shift it. Then 10 is not greater than 12. So I am here now, right now. Okay, I have moved all the elements. Now right now here 10 is not greater than 12. So this place is free. So this place store the element 12. So all these elements will be shifted and 12 will be inserted here. So I don't have to search and find out its position. From the last, go on shifting larger elements. Then wherever you get any element smaller than the element that you are inserting, insert the element there. So all the larger elements are shifted on the right hand side. That's all. This is insertion. Then let us also see insertion in a linked list. So I have taken a linear singly linked list, and this is a list of sorted elements, and I want to insert 18. In a linked list, we don't have to shift the elements. Shifting is not required. Then we have to find out where this 18 should come. Like in this linked list, 18 should come after 15 or before 20. So I should find out its position and insert it. That's all. So for finding its position, I will take a pointer to traverse a linked list. Then also I will take one tail pointer. Now I am showing you the procedure how to insert it. Check P's data, that is smaller than this one. So move P to next, but before that bring Q upon P and then move P. This is smaller than 18. So again move P. But first bring Q upon P, then move P. Now P's data is smaller than 18. Then again move P and Q. So first Q, then move P. This is still smaller. 15 is smaller than 18. So move Q upon P and move P to next. Now 20 is greater than 18. So we have found the first element which is greater than the key element that we are inserting. So we found its position. So it should be after Q. So for that, take one more temporary pointer and create a new node. Insert this value 18. Then make this T's next point on P and Q's next point on T. That's all. This is inserted. Now if I start from here, 2 to 6, 6 to 10, 10 to 15, 15 to 18, 18 to 20. So 18 is inserted in a sorted position. So in a linked list, we have to find out its position and then insert. Whereas in an array, we don't have to find the position. Simply shift the elements, and once you get a smaller element, then insert. And once you have finished shifting all larger elements, then insert at a free space. So what is the time taken for insertion in an array? Shifting of elements. How many elements? Some elements are shifted. So n depends on the number of elements. Maybe 0 elements are shifted, maybe all elements are shifted. So it may be minimum constant, maximum n. Minimum constant and maximum n. Then here, find out the position using P and Q. So traversing takes time. Insertion takes constant time. Just we have to create a node and make links. So searching for a position takes time. How much time it takes? It will traverse a few elements. So let us say n. So it may either traverse all n elements or just one element. So it may be inserted before 2 also, right? So time may be minimum constant, maximum n. So inserting an element in a sorted list takes minimum constant time, maximum order of n time. So that's all. I have explained you what does it mean by insertion. Now I will explain you insertion sort. That will be very easy for understanding. Let us look at insertion sort. For explaining insertion sort, I have taken an array of elements. So 5 elements are there. To reduce board work, I have just avoided indices and even they are not required. Let us perform insertion sort. The very first thing is, I have 5 elements here. So we assume that this first element is already sorted. If there is only one element, then obviously it is sorted. So we assume that just the first element is sorted. Then the remaining elements are not sorted. So remaining elements will take out from an array and insert them on this side in a sorted list. So take out an element, insert this side. Take out an element, insert this side. So right now in an array, one element is sorted, 4 elements are not sorted. One element, that is 8, is sorted. So from the unsorted list, we'll take out an element and insert this side. Take out an element and insert this side. This is what the procedure is. So let us start the process. First step, I will insert 5. Insert 5. So for inserting 5, see, first element 8 is as it is. I am inserting 5. So the remaining elements as it is. Now the list will be extending to 2 elements. Now for inserting 5, check with this element. 8 is greater than 5. So shift it. Now check. There is nothing. There is nothing to check. So we have reached at the first place. So insert 5 at this place. So after inserting 5, the result is 5, then 8. Till here the list is sorted. Remaining 7, 3, 2, they are not yet sorted. So I have shown here how to insert 5, how to shift the element, and this is the result. So one element we have inserted. So this, let us call it as first pass. First pass. Then second pass. In second pass, let us insert 7. In the list, already 5 and 8 are sorted. Now we are trying to insert 7. So list will extend till here. And the remaining elements are these are not yet sorted. So 7 we are going to insert. So 7, take it outside. Now for inserting 7, start shifting the elements which are larger than 7 from right hand side. 8, it is greater. 5, no, it's not greater. So 7 should be inserted here. So the result after inserting 7 is 5, 7, 8 and 3, 2. Till 3 elements list is sorted. We will also analyze this one. See, how many elements were compared? Just one comparison. How many swaps? Means how much shifting? Only one element was shifted. So let us say one swap. Then in this second pass, how many elements were compared? In our example, only one element was compared. But at most how many? Both 8 and 5 can move, possible. If the number is smaller than 5, then both can move. So let us write down maximum comparisons and maximum swaps. So maximum comparisons are 2 comparisons and maximum swaps are 2 swap. Now we have to insert 2 more elements and sort 2 more elements. Let me continue with the rest of the elements. The resultant array, I will take it here. Now third pass, insert 3. So insert 3. So for inserting 3, take out 3 and the list size will be till here. This is a free space. Now start shifting the element. 8 is greater, shift it. 7 is greater, shift it. 3 is greater, shift it. Then 3 comes here. So after shifting and inserting 3, the list looks like this. Till here the list is sorted. 3, 5, 7, 8. Then this is 2. Then here, how many comparisons and how many swaps are done? 3. 3 comparisons and 3 swaps, right? These are maximum. Now one last element is remaining 2. So this is the fourth pass we will perform. Insert 2. We will insert 2. So in this array, when we insert 2, from this side we will take out 2 and the list size will be maximum now till the last element. Presently sorted elements are these, that is 3, 5, 7, 8. This is a free space. Now start comparing and shifting the elements. 8 is greater than 2, it will shift 7 also and 5 also and 3 also. Then 2 will come at this place. After shifting and copying the elements, final array looks like this. 2, 3, 5, 7, 8. So that's it. This is sorted. We got a sorted array. So every time from right hand side we are taking out an element and inserting it on the left hand side. Left hand side list is always sorted. Now lastly, what are the number of comparisons? 1, 2, 3, 4. 4 comparisons we have done and maximum 4 swaps. Now let us do some analysis. So first of all, how many passes are required? Number of passes. Number of passes. 1, 2, 3, 4. 4 passes for 1, 2, 3, 4, 5 elements. 5 elements, 4 passes. Means 10 elements, 9 passes. So for n elements, how many passes? N minus 1 passes. N minus 1 passes required. Then how many comparisons? Number of comparisons. So find out number of comparisons. Let us check here. In the first pass, 1 comparison was done. And second pass, 2 comparisons were done. Third pass, 3 and the fourth pass, 4. So I'll add them. 1 comparison, 2 plus 3 plus 4. As there are 5 elements, 4 passes, so up to 4. N elements, n minus 1 passes to up to n minus 1. So this is n into n minus 1 by 2. So this polynomial is of degree square, order of n square. As the number of comparisons are taken as the time complexity of algorithm, so time complexity of insertion sort is n square. Maximum time taken by insertion sort is n square. Now what about the swaps? Here 1 swap, maximum 2 swaps, right? Then 3, 4 swap and 4 swap. So for swaps also same as number of comparisons. So number of swaps for n elements, it will be 1 plus 2 plus 3 plus goes on to n minus 1, and this is n into n minus 1 by 2. So this is n square swaps. So maximum swaps are order of n square. So this is about comparisons and swaps. We have to check whether it is adaptive and stable or not, but before that I will tell you few important things about insertion sort. First thing, if I perform just 1 pass, what is the result? See, after the first pass I got 5 and 8. Is it useful anyway? Can I say that the first element will be smallest element? No, we cannot say that. That is not the smallest element. If suppose I have one more element, 9 here, can I say 8 is the largest element? No. So intermediate results, that is just 1 pass or 2 pass, will not give you any useful result in insertion sort. Like in bubble sort, if we perform 1 pass, we get the largest element, 2 passes, 2 largest element. But insertion sort, you will not get anything useful. Then second important thing about insertion sort. We have seen insertion in an array as well as insertion in a linked list. So in an array, we have to shift the elements, but in a linked list, we don't have to shift anything. So the benefit of insertion sort upon linked list is that you don't have to shift the elements. Without shifting, you can insert. So insertion sort is more useful or more compatible with a linked list than array. Or I should say that insertion sort is designed for linked list. Yes, it is designed for linked list. So remember this point. For sorting linked list, insertion sort is better. Now next I will write down the algorithm for insertion sort. Then later we will analyze rest of the things. So here is a function for insertion sort which is taking an array and number of elements. In our example, the size of an array is 5. So n is 5 here. So let us assume that this is 5. But the indices are from 0 to 4 only. Now first is for loop for passes. How many passes for n elements? N minus 1 passes. But if you see the passes, in first pass, which element we are trying to insert? That is second element at index 1. So we are trying to insert this one, right? So this is index 1. So we don't have to start from 0, we have to start from 1. So insert the element from index 1, then 2, then 3, then 4. So this loop should start from 1 onward. So I takes values from 1 and I is less than till 4 it should go. So less than 5, less than n. So till 4 it will go, then I plus plus. So from 1 to 4, because at 0th index we have the first element and that we are assuming it's already inserted. So we are starting from this one. So this is for repeating passes. Then in each pass what we are supposed to do. Then I will take one example here. From that we will learn what we should do in every pass. Then we will write on the code. Now I have an example, an array of size 7. In this already till here the elements are sorted, that is 0 to 5. Now I am inserting 10. So take out 10 in some variable, let us say x. So right now I am inserting this element. So this I is present here. I is pointing here. So this is the element that I am inserting. So that element I have taken in x. Now I have to shift the elements and make this 10 insert in a sorted position. So right now this I is on 6. Now what is the procedure? So I should start shifting from where? This element onward. So I will take j here. J is I minus 1. Yes, the first thing I need is j. J is I minus 1. Yes, I need this j. And also I should take this last element wherever I is pointing, that in x. So yes, I will do this also. X assign a of I. That is the element that was present here, right? So I am taking in x. So I am assuming that it's not there. Then what is the procedure? I have to shift all greater elements. So I should compare a of j with the element x. This is greater, so shift it and j minus minus. This is greater than this, shift it, j minus minus. This is greater than this one, 10. So shift it, j minus minus. This is greater than this one, so shift it, j minus minus. Now this is small, stop. So the procedure is very simple. Go on shifting the elements as long as a of j is greater than x. So yes, while a of j is greater than x, go on shifting the element. So wherever j is pointing, move the element to the next location. A of j plus 1 should be copied with a of j, as well as j should be decremented. This is what I have to do for shifting the elements. And right now, this 20 is moved, 18 is also moved, and 14 is also moved, 12 is also moved. This place is free, right? This place is free. So this element, we got it smaller. So this element 10 should be inserted at which place? J plus 1. So once you come out of this loop, the element should be inserted at j plus 1. J plus 1 assign x. That's all. I have stopped this loop also. Now one more thing. This place I left it empty. So let us observe. Suppose this is not a 10. If this is 2, then what happens? From this point, if I continue, 8 is greater than 2. Shift it. J minus minus. 6 is greater than 2. Shift it. J minus minus. So j became what? Minus 1 now. So stop. So when j becomes minus 1, stop. Means continue as long as j is greater than minus 1. So one more condition I should write down. j greater than -1 and this condition. So this is the algorithm for insertion sort. We found that the time complexity of insertion sort is n square, and here from the code if you see for loop, then inside that while loop. So two nested loops are there, so this is n square. So from the code also we can say it is n square. So next thing that is remaining is we have to check whether it is adaptive or stable or not. Let us check whether insertion sort is adaptive or not. See, we have already learned about insertion sort procedure. It will start inserting the element from second element onwards. It will start inserting on the left hand side. So let us perform insertion sort procedure on this list of elements. So leave the first element, second element take out, then check, is it greater than 5? No, 5 comes here only. Only one comparison. Then 8, let us insert this and check, 5, is it greater than 8? No, that is smaller. So insert 8 here only. We perform one comparison and there is no shifting. Then take out 10 and compare with this one. Try to shift. This is not greater than 10. So no shifting required. Then write down 10 here only. Then 12. This is I, right? This is J. This is X. 12. A of J, is it greater than X? No. No shifting required. This condition fails, right? No shifting required. Then write down the element at J of J plus 1. A of J plus 1, copy the element 12. So for every element we perform only one comparison and there was no swapping at all. So only one comparison for how many comparisons now total? Number of comparisons for one element, one comparison. But we have done it for only 4 elements. We have not done it for first element. So n minus 1 comparisons. So this is order of n. And how many swaps we have done? Number of swaps. Swaps here are shifting. Have we shifted any elements? No. 0 elements are shifted. So it is order of 1. So the time taken by insertion sort is order of n if the list is already sorted. So it is taking minimum time. Yes. So insertion sort is adaptive. So yes, it is adaptive. Insertion sort is adaptive. Now one more thing. Did we use any flag or anything like this, like we have done in bubble sort? No, we did not use anything. So by nature, in its nature, it is adaptive. So we did not made it adaptive by introducing something extra. By nature, it is adaptive. Yes, insertion sort behavior itself is adaptive behavior. So insertion sort time, if you take, minimum time is order of n. Maximum time is order of n square. And swaps, minimum swaps are order of 1 if the list is already sorted. Maximum swaps are n square if the list is reverse sorted. So if the list is in descending order, then it requires maximum comparisons and maximum swaps. If it is in ascending order, then minimum comparisons and minimum swaps. So I can say that best case of insertion sort is list is already sorted in ascending order, and the worst case of insertion sort is list is already sorted in descending order. We are sorting in ascending, right? But it is already in descending, then all elements we have to reverse. The next thing we have to check whether it is stable or not. Now let us look at this. So in this example, we can see that the list is already sorted till here, and this is the last element to be sorted. And that element is duplicate, right? This is one black color 5 and this is red color 5. So that 5 I have to insert. So let us see how to insert and what happens after insertion. I will insert 5, take out 5, right? Now I have to find the place of 5. Check. So shift the elements. 12 is greater, shifted. 10 is greater, shifted. 8 is greater, shifted. 5 is not greater. So this 5 will come here after this black 5. So in the original list, first was black 5, next was red 5. So in sorted list also it is same. It will not shift the elements if it is equal. So that's how it keeps the element stable. So yes, insertion sort is stable. So we have checked that it is adaptive as well as stable. In this video, I will show you a insertion sort algorithm. Already we have seen insertion sort program or algorithm. I will write on a function for that one. See, this is the project for sorting. Already I have started it at the time of bubble sort. So I am using the same project. Already I have the list of elements here and the number of elements are 10. And this loop is for displaying all the elements. Now here I will write on a function for insertion sort. So as discussed, function returns void insertion. I'll call it as insertion, just takes parameter a and number of elements. Now inside this I need few variables like I, j and x. Now I should run a loop for the passes. So for that I should perform n-1 passes. So actually I starts from 1 onwards and I is less than n I plus plus. n-1 passes are there. So that's the reason I is starting from 1 onwards instead of 0. Then initially j should be assigned as I minus 1 and x I should take a of j, the element that I have to, a of I, that is the element that I have to insert. Then for shifting the elements we have used a while loop while j is greater than -1 and a of j is greater than x. And every time we are shifting an element at a of j plus 1, that is at the next location, I'll copy the element of j. So I'll shift the elements. Then j minus minus. Then after the end of loop at a of j plus 1, I should copy the element that is taken in x. That's all. This is the insertion sort. Let us call this from here main function and see whether it sorts all the elements or not. Insertion array of elements and the number of elements are n. Let us run the program. 2, 3, 4, 5, 6, 7, 9, 10, 11, 13. Yes, it has sorted. That's it. It's working perfectly. So that's all in this video. You can write on this function and try it by yourself. Now let us compare bubble sort and insertion sort. We have already finished these two. Let us compare them. See, the first thing is minimum number of comparisons in bubble sort. If the list is already sorted, then the minimum number of comparisons are n. Then what about in insertion sort? If the list is already sorted, then again it also performs only n comparisons. Actually it is n-1. So let me write it as order of n. Then maximum number of comparisons, n square comparisons. This also n square comparisons. If the list is already in descending order, then maximum comparison. So same case. Case is also same. Time is also same. See, let me write the case here. Already in ascending, in descending. If it's in ascending order, then minimum time, and descending order, maximum time. Then minimum swaps, 0 swaps actually, so constant, 0 swaps. When, if it is in ascending, this is the case, right? This is the case and this is the swap. This is the case, this is the time. Then maximum swaps, n square, and this is also n square. And when this is in descending. Then adaptive, yes, adaptive, this is also adaptive. Stable, yes, this is also stable, this is also stable. See, almost all the properties are matching. They are similar. Yes, they are similar. Their properties are similar. These are only two algorithms which are adaptive. No other sorting algorithm is adaptive. These are adaptive. And these are stable also. But there is one more algorithm like merge sort that is also stable. So only two algorithms are adaptive. Only three algorithms are stable. Out of those, these are two which are stable. Next, linked list. Is it suitable for linked list? No. Is it suitable for linked list? Yes. Here you don't have to shift the elements or create a new linked list, but here you may have to shift the elements. Then k passes. Are they useful? Yes. Gives you k sorted elements. Here, are they useful? No. K passes are of no use. If you perform two passes, you get two largest element. Here you don't get it. That is comparison of bubble sort and insertion sort. So this comparison also very useful. That's all about comparison. The topic is selection sort, and this is the n square algorithm. It comes under comparison based sorting. I have taken a list of elements. I have to sort them. Why the name selection is taken, we have to understand that. So while explaining the procedure, I will tell you what is the meaning of selection. So let us start the procedure. This algorithm also sorts the element in passes. In each pass, one element will be sorted. Just like bubble sort and insertion sort, for n elements, n-1 passes are required. So let us perform first pass. From that we will learn everything about selection sort. So let us perform first pass. From that we will understand the working of selection sort. Now for sorting these elements for the first pass, I will take this list vertically. So I will write the elements. So I have a list ready here. Let us perform first pass. In first pass, we will select first position to find out an element for that position. So I repeat, I stress on the point, we select a position. Yes. So let us take I here, select a position. I is pointing on a position, that is index 0. Now who should come at this place? The smallest element in the list should come at that place. So find out minimum element. Find out whichever element is minimum. So for finding out minimum element, we will take two pointers, k as well as j, 2. Both of them will be on the same position wherever I is pointing. Now let us see how to find out minimum. Move j to the next element and check whether this is smaller than where k is pointing. Yes. So bring k at this place. So j will find out minimum element, and if any element is found, it will bring k there. Continue. J moves to the next location. J is pointing on this element. Is it the element smaller than where k is pointing? Yes. So call k here. Ask it to stand here. This is the smaller element we found. Then move j to the next element. J is here. Is it smaller than the element where k is pointing? Yes. So call k here. Ask it to stand here. We got a still smaller element than where you are pointing. Now j moves to the next element. Is it smaller than the element where k is pointing? No. Move to the next location. Is it smaller than the element where k is pointing? No. So don't move k. Continue. Next element. Now j is at index 6, so it is out of the list. So we have finished the entire list and found out a smallest element where k is pointing. So just observe one thing. Just we found out which is the minimum element and we got its index. We have not swapped any elements. We did not swap any element. Right. Then interchange the element from I to k. Then the new list will be 263, 854. So 8 is brought in place of 2 and 2 is sent there. So 2 and 8 are interchanged. Now this is the result of the first pass and this element is sorted. First element is sorted. So in one pass we got one element sorted, and that is the smallest element in the list got sorted. We got the smallest element in the list. So what we did is we selected a position, that is first position, that is index 0, and found out an element for that particular position. So we got a smallest element for that position. Now this was the first step, first pass. Continue same thing. Perform second pass. So quickly I will perform remaining passes. This is second pass. First element is already sorted. Now select the next position. So I will be pointing here. Now take j as well as a k also here only. J and k there only. Right? Then using j find out the element that is smaller than this 6. Is it smaller than that 6? Index 2, right? We are on index 2. Yes. So bring k also here. Then move j. Is it smaller than 6? No. Is it smaller than 6? No. Is it smaller than 6? No. J has finished the list. So finish the list means we got the smallest element. What is that? K, that is index 2, that is element 3. Interchange. So these two elements will be interchanged and the new list will be 2, 3, 6. These are interchange and 8, 5, 4 as it is. So these two elements are sorted. Now let us perform third pass. Take I on index 2, that is third element, because already two elements are sorted. I is here, and make j as well as k, both of them point there only. Now start using j to find out the element that is smaller than this. Is it smaller than that? No. Is it smaller than that? Yes, 5 is smaller than 6. So bring k here. Then continue. J, is it smaller than where k is pointing? Yes, 4 is less than 5. So bring k here. So end of list, and we got a minimum element at index 5. So interchange these two. Then the new list will be 2, 3. This will interchange. So here 4, then 8, 5, 6. Now 3 elements are sorted. Next we have to select a fourth element, that is index 3. We have to sort this one. We have to find an element for this position. So k and j will be pointing there only. Find out a smaller element. Is it smaller than that? Yes. So bring k here. Is it smaller than 5? No. So list ends. So this is the smallest element in this list. Interchange these two. So the list will be 2, 3, 4, 5, 8. These are interchange, and 6. So these 4 elements are already sorted. Now only 2 elements are remaining. Then select next index 4 and find out the smallest element for that position. So start k as well as j. Then j is here. Is it smaller? Yes. So bring k here and end of the list. Then interchange. K is here, so it is interchange. So the new list is 2, 3, 4, 5. This two will interchange. So 6, 8. This was fourth pass and this was fifth pass, and this is the result of the fifth pass. All elements are sorted. We sorted total 5 elements, but the 6th element will automatically get sorted. I'll separate it so that you can see it clearly. So total 5 passes, the last thing is sorted order. So once again, we were selecting a position and finding the element for that position. It is just like, imagine there are some students in a class and this is the first seat in the class. I have to find out who should sit here. So I selected the seat and finding out who should sit here. Okay, I'll ask the student to come and sit here. Maybe based on height, based on the marks, or based on roll number, whatever it is. I'll select a seat and find a student who should sit here. So we selected a position 0, that is first position, that is index 0, and find out which element should come there. So in the entire list 2 was minimum, so 2 was brought there. That's it. So selecting a position, finding an element. Now let us do some analysis. Find the number of comparisons and number of swaps. See, in first pass we compared almost all elements. So total 6 elements are there. So 5 comparisons we have done. So comparisons were 5, and number of swaps. How many swaps we have done? We have performed just one swap. Remember this, one swap. And here at most 4 comparisons and just one swap. And here 3 comparisons and just one swap. 2 comparisons, one swap. 1 comparison, one swap. So if you observe the comparisons 5, 4, 3, 2, 1. So total number of comparisons I will write down here. Number of comparisons 1 plus 2 plus 3 plus goes on. For n elements, how many comparisons will be there? N minus 1. So this will be n into n minus 1 by 2, and this is order of n square. So we have already done this type of analysis in bubble sort and insertion sort. Here also it is same. Number of comparisons are n square, so the time is n square. Then how many swaps? In each pass just we are performing just one swap. So number of swaps are For n passes, n minus 1 swap. So it is order of n. Yes, this is more important about selection sort. For n elements, only n minus 1 swap. So order of n swaps. So this is the only algorithm which sorts the elements with minimum number of swaps. See, to avoid swaps, we have taken j as well as a k. We find the index. Once we found the index, then we interchange. Will not be interchanging every time. So we can avoid interchanging of elements with the help of extra variable k. So selection sort is good for less number of swaps. Next, one more important thing about selection sort. See, if I perform only one pass, then what I get? Smallest element. If I perform just two passes, then what I get? Two smallest element. So it means if I perform k passes, k number of passes, then I get k smaller elements. So yes, just like bubble sort, there we were getting k largest element. In selection sort, we get k smaller elements. So intermediate results of selection sort are useful. Now next is, we have to check whether it is adaptive and stable or not. Let us look at algorithm for selection sort. So we have already seen selection sort. In each pass, it will select a particular position or an index and find out a smallest element that should fit in that index. So for writing an algorithm, I have taken an example. We will trace the algorithm here and simultaneously I will write down the instructions there. So here we have number of elements that are 10. Now let us start. See, for n elements, as we need n minus 1 passes, in each pass we will select a particular index. So for that we have taken I, that will be selecting an index. First time we will find out smallest element for this index 0, then next for 1, then next for 3, so on. So we have to do it for n minus 1 time. So this is done using for loop. So this is for passes. So I will write a for loop here. This for loop is for passes. For I assign 0, I is less than n minus 1, I plus plus. So this will be starting from 0 and continuing. Now we want two more integer pointers that are k and j, that should also start from here. K and j should be initialized with I, and this j should scan through the list of all the elements up to n to find out a smaller element. If any smaller element is found, then k is brought to that location. So for scanning through all these elements to find the smaller element, I have to use again a for loop for j also. So I will write on one more for loop for j. See, for j and k both are starting from I, and j is incrementing every time and it's going till n, means less than n. So it will be stopping at 9. Now in this loop, I have to check for the element. If the element wherever j is pointing, suppose j is right now here, I have to check if this element is smaller than where k is pointing. If so, k should be brought at j. So that's what I will write here. If a of j is less than a of k, then bring k upon j. Make k also point there. So k will also move to this location. So this process should continue. And once this for loop ends, k will be pointing on a smallest element. So right now in our example, k will point on this is smallest element, right? And j has finished the array. So this is the smallest element. So this element should be swapped with the element at I. So I will simply write a function swap here. Swap a of I with a of k. A of I and a of k are swapped after this for loop. That's all. This is the end of this for loop and end of this function. So that's all. This is the algorithm for selection sort. Now let us check whether selection sort is adaptive and stable or not. So first we will look at adaptive. Adaptive means if the list is already sorted, then the algorithm should take minimum time. I have taken already sorted list. Now what is the procedure of selection sort? It will select the first position and find out an element. So what is the smallest element? That's same. So if I use k and j will be going on checking all the elements, but k remains there only because no element is smaller than 2. So then it will interchange with itself. Is there any way to find out that list is already sorted? Is there any way? So if I say that if the element is swapping with itself, means it's already sorted. So if suppose this is not sorted, this is 5. Then if that is getting swapped with itself, then how I can say that rest of the elements are already sorted? We cannot judge. See, in bubble sort, we identify that no swap means it's already sorted. So that same logic we cannot apply here, and even we don't find any method to check whether it is sorted or not. So selection sort is not adaptive. It's not adaptive. If the list is sorted or not sorted, it's going to take always n square time. Then second one, whether it is stable or not. So for stable example, I have taken a list. I have duplicate values 8 and one more 8. First is black 8, next is red 8. Let us perform one pass of selection sort. We select this as an index. Then we mark k also here. Then we search and find out the smallest element, and wherever the smallest element is found, k will be pointing here. So here we have a smallest element in the entire list, that is 2. So once the element is found, it is interchange. Now let us see the list. This 2 will come here, then 3, then 5, then red color 8, then 4, then black color 8, then 7. Now you can see that this 8 is first and this 8 is next. So this black was first, then was red. Now red is first, then black is next. So they have changed their order. So original order is lost. Just one example I have shown you. In this example, it is lost. So we cannot trust selection sort to be stable. So yes, it is not stable. It will not preserve the order. So that's all about selection sort. Two strong points of selection sort. First one is it performs minimum number of swaps, and second is the intermediate results of selection sort gives useful results, that is k passes gives k smallest elements. In this video, we'll see a algorithm or a function for selection sort, which we have already discussed on whiteboard. I'm using the same project that is used for sorting. So already I wrote bubble sort and insertion sort. It's the same program. So inside the same project, I will add one more function that is for selection sort. So let us write selection sort. It takes an array of elements and the number of elements n. Now I need few variables like I, j and k. Then for the passes, I should have I starts from 0. I is less than, I need n minus 1 passes, so I plus plus. So it is less than n minus 1. Then next for loop, that is for each pass, j as well as k should start from I, and j should reach till last element and j plus plus. And every time we check that if the element at a of j is smaller than element at a of k, then we will bring k at position j. And this inner for loop is for a pass. After the end of the pass, we will swap the elements at a of I and a of k. So swap function already is available. So ampersand a of I and ampersand a of k. That's all. This should sort all the elements. Already we have seen it's working. Now here inside the main function, I will call selection sort by passing array and the number of elements, and here it is displaying all the elements. Let us see whether it will sort the elements. Yes, 2, 3, 4, 5, 6, 7, 9, 10, 11, 13. It has sorted. Let us change some elements, like this is 16 and this is 24 and this is 12. Now let us run and see. I have changed few elements. So 3, 5, 7, 9, 10, 11, 12, 13, 16 and 24. Yes, it is working perfectly. So that's all. These are all simple functions. That is a simple function procedure for selection sort. So that's all in this video. Yeah, our next topic is quick sort. This is a mostly discussed one and most famous sorting technique, and sometimes it is believed to be a difficult one, but actually it is very easy and very interesting. So as in the previous sorting techniques, I was explaining you the basic idea behind the sorting method. Here also we will understand what is the basic concept behind this technique. So let us understand the basic idea upon which it works. So for explaining the basic idea, I have few example list here. Now I have few questions for you. In the first list, find out which element is already in a sorted position, which is already sorted. Just I want one element. In a single glance, you tell me the answer. Yes, you are right. 10 is already sorted. Rest of the elements are not, may or may not be sorted, but 10 you got it. That's fine. I don't bother about other elements. 10 we got it. That's enough. Now let us go to the second list, and in a single glance, just check it and tell me which element is already sorted. Just I want one element. Yes, you are right. So it is 90. 90 is already sorted. Now in this list, in a single glance, find out which element is already sorted. Yes, 50 is already sorted. Maybe other elements are also there. I don't want that. I am looking at 50, right? Now on what basis I am saying that 50 is sorted? Okay, this was correct. This is smallest and it's in the beginning, and that is largest, it is at the end. So they are sorted. On what basis I can say 50 is sorted? Because 50 is at a position where all the elements before 50 are smaller than 50, and all the elements after 50 are greater than 50. So that's how 50 is in a sorted position. If I sort this list, 50 will be a fourth element in a list. Definitely it will be fourth. Because there is no other element which is smaller than 50 that will come on this side. There is no other larger element than 50 which will come on that side. 50 remains in its own place. So 50 is already in its sorted position. So let me repeat the idea. Quicksort works on the idea that an element is in a sorted position if all the elements before that element are smaller, all the elements after that element are greater. Then we say that element is in a sorted position. So that is the idea. Now I have one example to give you a clear picture of quicksort. See, these are students and their heights are different. Suppose teacher wants them to stand in an increasing order of their height. So teacher has two options. Teacher can show the position of each and every student. Teacher can decide who should come first, who should come next behind that, and teacher can guide all the students to form a line in the increasing order of their height. So teacher is sorting them. Second option is a teacher can ask the student to arrange by themselves. So you tell me which one will be faster or which one will be quick. Teacher showing the positions and sorting them, or students finding their own places? Yes, definitely student finding their own places is quick. Maybe you have heard a statement from your teacher that students quickly form a line in increasing order of your height. So that is quick. So one more thing I want to add here. Quick sort doesn't mean this is fastest sort. No, this is not the fastest sort. After analysis, we will understand whether it is fastest or not. Now let us see how students will arrange themselves. Suppose these are the students and this is yourself, right? You have to find a place. Where you should be? You should go and stand in a line such that all those students who are shorter than you should be on the left hand side and those who are taller should be on the right hand side. You will try to find your place. That's all. So you are supposed to stand in your sorted position. So for that, what you do, you check with your friend, you check with other students and you tell him that, see, you are taller than me, please you go at the back. And you ask this guy, you are shorter than me, why don't you come and stand in front? And you ask this one also, you are shorter than me, come and stand front. You ask this taller person to go and stand at the back. So in this way, you try to arrange other students to find your own place. Yes. That's what the approach of quicksort. Now I'll extend this example a little bit to give you the complete idea of quicksort. Suppose you are supposed to stand in this line, so you are pivot element. Then from this side you have to check if anybody is taller than you should go out on that side, and from that side you will check anybody is shorter than you, he should come on this side. So you will take I and J here. Using I you will find out anybody taller, yes he is taller. Using J you will find out anybody shorter, yes he is shorter. Ask them to interchange their places. So then again move I to next place, then move J to next place and check, is he taller than you? No. Is he taller than you? Yes. Is he shorter than you? Yes. Ask them to change their places. In this way, from both the sides, from I and J, you will check if anybody taller, anybody shorter. Ask them to change their places, so that at one point you can say that this is my sorted position. How do you confirm you are in a sorted position? Suppose you are standing in a queue, in a line, and say that I am standing in my proper position. Because all the people in front of you are shorter, all the people at the back are taller. Whether they are sorted or not, that is not my business. These are sorted or not, and it's not my business. I am in my position. That's how you will find your position as a student standing in a line. That's all. This is the idea. Next, I will take some example and I will sort the elements, and also I will show you the algorithm for quick sort. Yeah, I have taken the list of elements here and I want to sort the list. So let us see the procedure. Apply the procedure of quick sort and sort one element first. So let us do it. See, the procedure is first element in the list, we select it as pivot, or pivot, whatever you say. So this is pivot element. First element is pivot. So what is this pivot? See, I have given the example of students and you are finding your place. So yourself was pivot. So who is going to find out the place now? 50 has to find its place. So that is pivot element. So we have to find out the position of 50. So for that, all the elements smaller than 50 should be on this side. All the elements greater than 50 should be on that side, right? On the right hand side. Left hand side, smaller elements. So for that, we will see if there are any larger elements on this side. And from that side, we will see are there any shorter elements, right? If so, we will interchange them. So for that, we will take I here, that will look for greater element. So if any greater element is found, it will stop and then try to interchange. Then we'll take J from here, that will be looking for any smaller elements. So if any smaller element found that side, it will interchange with the element. I will be looking for any element that is greater than pivot. So it must get some element that is greater than pivot, right? Then only it will stop. And J will be looking for an element smaller than or equal to pivot, so that at least it will come and stand at this pivot itself. So pivot is equal to itself, so it will stop there. I will be looking for a greater element only. J will be looking for smaller or equal element. Now when I is looking for greater and greater, suppose no element is greater than pivot, then there should be something to stop I. So for that, I will take infinity at the end. Without this also you can do. I am showing a method with infinity. So what is that infinity? End of list marker. Some maximum integer, maximum number you can take, or some marker. So largest number, like if integer is 2 bytes, then 32767, that is the largest integer you can take. Let us start. So we selected pivot, I and J also initialize. Let us start. Using I, find out an element which is greater than 50. Is it greater than 50? Yes, we got the very first element greater than 50. Using J, find the element that is smaller than pivot, that is 50. Decremented. Yes, we got an element that is smaller than 50. So what that smaller element is doing here, what this taller person is doing here, ask them to interchange their places. Okay. Now the next list will be 50, and here comes 30, this is 60, and 90, 40, this is 80, 10, 20. So 70 will come at this place. Infinity is as it is. I is still here, J is still here. Let us perform next step. Again continue I. This is greater. Yes, stop. This is smaller. Yes, it is stop. See, I have taken the elements, most of the greater element this side, smaller that side. So we can see more number of swappings. We got a greater element here. We got a smaller element there. What you are doing here, you come and stand. This person, please go their side because you are taller than me. I am pivot 50. Okay, interchange. This is 50 and 30. 20 will come here. Remaining as it is. 60 will take this place. Infinity. I is pointing here. J is pointing here. Continue. Move I. This is greater than pivot. Yes. Move J. This is smaller than pivot. Smaller than 50. Then interchange them. 50, 30, 20 as it is. At this place 10 will come here. These two as it is. 90 will take the place of 10. Infinity at the end. This is pivot. I is here. J is here. Continue. Find the element which is greater than this one. Is it greater? No, this is not greater. Move. So I should move if it is smaller. I should stop if it is greater. So it should continue. If it is smaller or equal, it should continue. Right? It should stop when it is greater. Remember this. This is a confusing point sometime for the students. Then same way, using J, I have to find out an element that is smaller than this one. So J will decrement. Is it smaller? No. So if it is greater, continue. Is it smaller? Yes. Stop. If it is smaller or equal, stop. If it is greater, it should continue. Then, now if you observe, I became greater than J, means we have checked the entire list of elements. Nothing is left. We have checked thoroughly. So we have interchanged all the elements. See, I has started from this side and J has started from this side. Now they both met at some place. So how I became greater than J? So we have checked the entire list. Now do what? Interchange pivot element with Jth element. So 40 will come this side. 30, 20, 10 as it is. This is 50 and remaining elements as it is. This is infinity. This is sorted at J. So one element, that is 50, we got it sorted. And the rest of the elements, if you see, all small elements this side, all greater element that side. So 50 is sorted. So now one element 50 is sorted. What about rest? We have to sort this list. Still we have to sort this list. And still we have to sort this list. So list is partitioned here, splitted here. So this position we call it as partitioning position. List is getting partitioned here. So some elements on this side, some elements on this side. In my example, I got four elements on both sides. It's not necessary that it is always in the middle. It can be anywhere. But the list is partitioned into two. And we have to sort this one also, this one also. How will you sort this? Quick sort again. Quick sort on this, quick sort on this. On both we will perform quick sort. So it means quick sort is recursively applied on left hand side and right hand side. Yes. So can quick sort work on few elements? Yes. Two elements are there, it can work. One element, no need to sort. Minimum two elements must be there for performing quick sort. I'll show you that. And one more point. Who is infinity for this one? This value, largest value that we have added as an end of list marker. Then who is infinity for this list? It's ending here. Where is infinity? So this sorted element 50 will act as infinity for this left hand side list. So that's all. We will see this. Now one last thing. This entire procedure of selecting pivot and taking I and J, exchanging the element, that is smaller and larger elements, then finally bringing pivot at a partitioning position. This entire procedure is called as partitioning procedure. So it's partitioning procedure. So quick sort uses partitioning procedure for sorting the elements. And also it is recursive. So first I will write on partitioning procedure, the one that we have seen. Then I will write on the quick sort recursive algorithm. Now we'll do analysis of a quick sort. Before discussing time and the space complexity, I want to discuss some example. See, mostly people get confused. If there are too few elements, like 2-3 elements are there, then how quicksort can work on it? So I'll take a small list of 3 elements and show you how quicksort can work on it, and also 2 elements and show you. So let us take 3 elements. Suppose the elements are 20, 10 and 30. This is infinity, this is pivot, this is I and J. This is the initial setup. We have to find the sorted position of 20. Right? So let us start. Using I, find out any element that is greater than 20. Is it greater? No. Is it greater? Yes, found. Using J, find out any element that is smaller than or equal to 20. Is it smaller? No. Is it smaller? Yes. We got the positions for I and J. But now I has become greater than J. If I is greater than J means this pivot will get swapped with the element at J. So 10 comes here, 20 goes there, 10 this side, 20 that side, 30 in its own place. This is infinity. From here the list is partition. There is only one element this side. There is only one element. Include this infinity is ignorable, right? So there is only one element. That's all. Now this one element is sorted, and on the either side we got one element. So this list is sorted. If we perform quicksort on this, quicksort on this, quicksort will not work upon them because it will work at least there are 2 elements. So this was the example of 3 elements. Now let's take the example of 2 elements. Suppose I have 10 and 20. That's all. This is infinity. How quicksort will work on this? First element is pivot. I is on first element, J is on infinity. Using I, find out an element that is greater than 10. This is found. Using J, find out an element that is smaller than or equal to 10. Is it smaller? No. Is it smaller? No. But it is equal. Okay, stop here. I became greater than J. So we will not swap I and J element, but we will swap pivot with J. Pivot is also same, J is also same. So it is swapped with itself. So like if this is low and this is high, so A of low is swapped with A of J. So same element will swap with itself. Nothing will happen. 10 remains there only. So now this is partition here. So this 10 is sorted. Then on that side we have just 20. Ignore infinity. So there is single element, no need to sort it. So that's all. It is working on 2 elements also. Now I'll take one more example. If the elements are already sorted in ascending order, then how quicksort works? So here is a list of elements which are already sorted, and if we run quicksort on this, let us see what happens. First it will select this as pivot, I here and J here. Using I, find out any element that is greater than 10. So this is found. Using J, find out any element that is smaller than or equal to 10. Is it smaller than 10? No, 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 no. Yes, equal. This is low and this is high, right? So J and I. So I became greater than J. So interchange pivot element with J. That is interchange element at L with J. So it is interchange with itself. Then the list is partition. How many elements we get on this side? Nothing else. Then how many elements on this side? We get all these elements. 20, 30, 40, 50 and infinity. So from here partitioning is done, right? You know the procedure. Partitioning is done. Left hand side, nothing. Right hand side, all remaining elements. That is, if you say these were n elements, then these are n minus 1 elements. Then next, we have to continue sorting. Select this as pivot. This is low and this is high. I is here, J is here. Using I, find out any element that is greater than 20. Yes, found. Using J, find any element that is smaller than or equal to 20. It's not smaller, not smaller, not smaller. Equal, found. I is greater than J. So we got a partitioning position. Interchange element at low with J. Means pivot element swapped with J. So it is swapped with itself. So no change, element remains there only. Partitioning is done. You remember J, partitioning is done. So how many elements on left side? Nothing is there on the left hand side. Remaining all on the right hand side. So the remaining elements are 30, 40, 50 and infinity. Now how many elements are there? N minus 2 elements are there. Then select pivot. I here, J here. Using I, find out any element that is greater than 30. So it is found. Using J, find element smaller than or equal to. Not smaller, not smaller. Yes, it's equal. So stop here. Interchange with itself. Partition the list. So 30 is gone. Remaining 40 and 50 are infinity are remaining. Now how many elements? 2 elements. Then select this as pivot. I here, J here. Move I to find greater element. Yes, found. Move J to find smaller or equal, same element. Partitioning is done here. What is left? 50 and infinity, one element left. For one element, no need of sorting. So you can see this is how quicksort is working on a sorted list. It means first time when n elements were given, next time nothing was there on this side, n minus 1 elements that side, then again nothing on this side, n minus 2 elements this side, then this has go on reducing, then finally 2 elements this side, right? No elements this side, 1 element this side and 0 element this side. Now let us find out the time. See what it is doing. First time n elements were compared. I was moved here, but j was brought from here till here. N comparisons. Again here also j was brought from infinity till this one. N minus 1 comparison. So as many elements are there, that many comparisons are done. So first time n comparisons are done, then n minus 1 comparisons are done, n minus 2, so on, then 2, then finally 1. So total how many? 1 plus 2 plus 3 plus goes on to n comparisons. I am adding all these comparisons. So this is how much? N into n plus 1 by 2. So this is order of n square. So this is the time complexity of quicksort. For what? Sorted list. If the list is already sorted. So actually this is the worst case time of quicksort. This is worst case. If the list is already sorted, it is taking n square time. And the list is sorted in ascending order. Then one conclusion, if the list is sorted in ascending order and we are trying to sort it using quicksort, it performs these many comparisons. So that are n square comparison. So the time complexity of quicksort is n square. I'll remove this, then we will see second case. I have taken a list in descending order. Let us understand how quicksort works on this one. Let us sort. Few elements I will sort. This is selected as pivot. I is here, j is here. Using I, find out any element that is greater than 50. Is it greater? No, not greater than 50. No, no, no. Yes, this is greater. Infinity is greater. Then using j, find any element that is smaller than 50. Is it smaller? Yes, this is smaller. But I became greater than j. So interchange pivot element with j. So if you send it here, then 10, 40, 30, 20 and 50 and infinity. This element is sorted, these elements are remaining to be sorted. 50 is sorted. How many elements on right side? Nothing is there. Infinity is not an element. So nothing is there on the right hand side. So if you see now, the previously I have shown you a tree. So this n, now this side n minus 1 elements, this side nothing is there. So as the list is partitioned, it is partitioned into 2. So but one of the list is empty, nothing is there. So on these elements if we perform, then 10, 40, 30 and 20 if I perform, this is selected as pivot, I is here, assume that infinity is there, j is here, okay. That 50 will act as infinity. So I will not show 50, I will show infinity only. Using I, find out any element that is greater. Using j, find out an element that is smaller than or equal to 10. Is it smaller? No, no, no. Yes, found. I became greater than j. So pivot element L is swapped with j itself. So one element is sorted. Remaining elements are these. So now this time left hand side nothing. Everything is on the right hand side. So on this side nothing. N minus 2 elements on this side. So if it is in descending order, then one time partitioning was done at the end of this list, right hand side. Then next time it was done on the left hand side. So if partitioning is happening on leftmost position or rightmost position, then the time taken by quicksort will be, if I continue this, you know the answer, n square. Yes. So the time complexity of quicksort will be n square. So this is the worst case time of quicksort because the partitioning is happening on any one end of a list and one of the list is being empty, all the rest of the elements are coming in one single list. So that's why time is order of n square. And this is worst case time of quicksort. So finally, now conclusion. Now one of the conclusion again. elements if they are in ascending order or descending order. Quick sort will take n square time. For the best case, assume that I have a list of 15 elements. I am starting index from 1 onwards. That is easy for understanding. We know arrays start from 0. Okay, don't get confused with that. I am taking from 1 onwards, so it's easy for understanding. So it is starting from 1 and ending at 15. And last is infinity. That is not a part of list. Just ignore it. So it's there, it's counted, but just ignore it. Now how quicksort works? When you give list of elements from 1 to 15, then it will perform partition and it will find the partitioning position and pivot is brought there and the list is splitted. So assume that list is splitted in the middle. Assume this. This is best case. It is splitted in the middle. If it is in the middle, then that will be position 8. So 7 elements on this side, that is 1 to 7. Then 7 elements on this side, that are 9 to 15. So list is divided into 2 equal halves. Then how many elements on this side? Okay. Then if quicksort is performed here, assume that again it is partitioning in the middle. This is assumption. It may or may not happen. This is assumption. If it is in the middle, then elements from 1 to 3 on this side, then 5 to 7 on this side. 3 elements here, 3 elements there. And on that side also assume that same thing is happening. So this is 9 to 11 and this is from 13 to 15. So this is at 12. So partitioning is done at 12. Then here partitioning is done at 2. So element that is 1 to 1 on this side and 3 to 3 on this side. Now these are 1 element only. And here partitioning is at 6. So 5 to 5 on this side, then 7 to 7 on this side. Then partitioning is at 10. So 9 to 9 on this side and 11 to 11. These are all single elements. Then partitioning is at 14. So 13 to 13 on this side and 15 to 15 on this side. So as quicksort is recursive, the order in which these calls will be made is this is the first call and this is the second call, third call and fourth call which will not do anything, fifth call, then sixth and seventh, eighth, then this will be a ninth call, 10th, 11, 12, 13 call, 14 call and 15 call. So as quicksort is recursive, I have written the order in which these calls will be made. Like this is the first call, second call, third call, fourth and so on. So already you know about the recursion, so how the calls are made. So this is how we are representing a tree based on the working of the quicksort. And we are assuming that partitioning is always done in the middle of a list. So half of the element left side, half of the elements on right side. Then how much time it will take? Now level by level if I compare, here how many comparisons are done? N elements are there, so N comparisons are done. Then the next level, this part is different and this part is different. Calls are different. This is second call, that is 9th call. But at this level, here half of the elements, here half of the elements. Total how many elements? Again N elements. But actually if you see, combined together, one element is less because 8 is already sorted. So anyway, I will not write N minus 1, approximately it is N only. Then in this level also, if I take up all those elements, 3, 3, 3, 3, so total 12 elements are there. So approximately 15 elements only, so I will take it as N. So that's all. In this last level, no work is done. So total how many comparisons are done? In this partitioning, elements are compared using I and J. So total how many comparisons are done? First time 15, next time here one less and here one less, then also they are reducing. But I am taking them approximately N only because reduction is not a huge reduction. Every level N comparisons are done. So total how many levels are there? See 15 elements. So you assume approximately 16 elements divided by 2, 8, 8, 8. Again divided by 2. So 4, 4. Actually we are getting 3, 3 because this is 15, right? Then again divide by 2. 2 elements. So finally actually we are getting 1 elements. Then 2 divided by 2. Finally 1 element. So this successive division by 2 is nothing but log base 2 for number of elements. So approximately log base 2. Approximately log base 2. Log of 16. Don't take 15. 16 is 4. But how many levels we got? Only 3. So log n minus 1 you can say. So log n minus 1 you can say. So basically you see the behavior. Elements are divided into 2. Then again divided into 2. So this is log. So n comparisons. How many times? N comparisons. So how many times? Log n times. So the time complexity of quick sort is n log n. So this is the best case analysis of quick sort. Now finally we will conclude the topic. For that I will remove this and I'll write down something here. Now in conclusion we will see what is the best case of quick sort. Best case is if partitioning is happening only in the middle. If partitioning is done in the middle. Then what is the best case time? Best case time is order of n log n. So best case is partitioning is always happening in the middle and the time taken in that best case is n log n. Then what is the worst case? Partitioning is on any end of a list. So that is either left hand side or the right hand side, left end or right end of a list. Then what is the time in that case? Then what is the time taken in that case? It's order of n square. So worst case is n square. Best case is n log n. Then what is the average case time? Average case time of quick sort is n log n. So best case is n log n, average case is n log n, but worst case is n square. And worst case will happen if the list is already sorted either in ascending order or descending order. So that's all about the time. See, what is worst case if the list is already sorted? This is the definition of worst case. What is best case? We don't know. But partitioning is in the middle. How are the elements? Are they sorted, not sorted? What? We can't tell what is the arrangement of element. But for some arrangement, if partitioning is in the middle, so their best case is defined in terms of partitioning position. Worst case is defined in terms of arrangement of element and also partitioning. But arrangement of element also we know. Here we don't know arrangement of element. Then next. See, in partitioning we are selecting first element as pivot. First element as pivot. Suppose from the list, if we select middle element as pivot, we can change. Yes, you can select any element as pivot. So you can bring this middle element as the first element, interchange with the first element and select this element as pivot. So the element will be this one. This element is brought here. We can select this one. So we can also select middle element as pivot by bringing it at a first position of a list. Then what happens? What is the benefit if you are doing this? If the list is already sorted, then where the partitioning will be done, it will be done in the middle only. Because we brought the middle element as pivot, where it will go and sit in the sorted list, it will go and sit there only. So partitioning will happen always in the middle. So instead of selecting first element as pivot, if we select middle element as pivot, if we modify this, then best case will be sorted list. When the partitioning is always in the middle, then the time will be n log n. So sorted list becomes a best case. Then what is worst case? Worst case will be partitioning at any end. So worst case remains same. But can you define it? No, it is not sorted list. Some other list, some list for which partitioning is always in the end of a list, either left end or right end of a list. That time is n square. First element as pivot, then partitioning in the middle happens, then n log n. How the list looks like? We don't know. First element as pivot, partitioning at any end, then worst case, n square. How the list looks like? Already sorted. Then change. Which element is selected as pivot? Middle element is selected at pivot. Then best case, n log n. Can you define the list? Sort it. Worst case, n square. Where the partitioning is done at any one end. Can you define the list? No, we don't know. So that's how By selecting middle element as pivot, we converted that worst case into best case now. It has become a best case. But still the worst case time of quicksort is n square for some order of elements. So we try to improve quicksort by changing the pivot, but still the time is n square. And lastly, there is one more idea about quicksort, that instead of selecting middle element as pivot, we can randomly select some element as pivot. So that is called as randomized quicksort. So here some changes we have to do, right? We are selecting first element, otherwise we can select middle element, or we can select the random element. So only this place, if you make some changes, then quicksort will change. If you are selecting randomly some element as pivot, then it is randomized quicksort. So for that also, best case time is n log n, worst case time is n square. We cannot define how it looks like, but partitioning will be in the middle, partitioning will be at the end. These are the two ways of defining best case and worst case, however the element may look like. Then one last thing I have to show you. One interesting comparison we will do here between selection sort and quicksort. Selection sort already we have studied. Let me show its behavior once again. In selection sort, we select a position, like this is index 0, we select a position. Then at this place, who should come, we find out the minimum element and bring it there. So we select a position and find out element for that position. The statement is very important. Again, I am going to repeat. In selection sort, we select a position and we find out an element for that position. But in quicksort, we select an element and find out the position for that element, where it should be in the list. Selecting a position, finding an element, selecting an element, finding a position. So the similarity between selection sort and quicksort is selection of what? Index element. So this quicksort is also called as selection exchange sort. And this quicksort algorithm uses partitioning. That is the reason it is also called as partition exchange sort. So three names for quicksort: selection exchange sort, partition exchange sort, or quicksort. So that's all about the analysis of quicksort. In this video, we will write a function for quicksort. So already we have seen the procedure. So we have written actually two functions for quicksort. One was partition and the other was recursive quicksort function. I will write on both the functions. So let us start writing a program for quicksort. See, already I have an array here. These are array of 10 elements. So what I'll do is, here at the last, I will add one more element, that is 65535. This is the largest positive integer, or else I can take int underscore max, that is maximum integer. So this will act as infinity. Now I have total 11 elements including infinity. As in the procedure, we were using infinity as the last element in an array. So that will help us to show the end of an array, that is, it's a delimiter for a list. Now let us write on the functions for quicksort. So the first function I will write on is partition. Partition function returns integer and it takes array of elements and low as well as high. That is the starting and ending point of a list. Now here inside this, I need some variables like pivot for taking a first element, that is pivotal element is a of low, and I need I that starts from low and j starts from high. Then using do while loop, we have written the code. So in do while loop, first we will increment I in a do while loop. So I plus plus, and this is while. See, I should move as long as the elements are smaller or equal. Means it should stop when the element is greater. So I should write on the condition for continuation, not for stopping. So I should say a of I is less than or equal to pivot. So if it is less, it will move, it will not stand. If it is greater, it will stop. Yes, this is perfect. Then do j minus minus, and here I should say while a of j is greater than pivot. So if the element is greater, j should decrement. If it is smaller or equal, it should stop. Yes. Then after that, we check if I is still less than j. If so, then we will swap the elements from a of I with a of j, address of a of j. Then swapping is done. Now I have to write the condition for while loop. So do while loop while I is less than j. When I becomes greater than j, it should stop. And when it has stopped and came out of this while loop, I should swap the elements, that is a of low, that is pivot element, with a of j. This is the last swap. Then it should return j. That's all. This is a partition function. This is a partition function. Already we have learned about this one. Now I should write on a quick sort function, that is a recursive function, void quick sort. It should take a array of elements and low and high. Then it should check that at least there are two elements, that is if low is less than high, then it should call partition by sending array and low and high. Then whatever the result is returned, it should take in a variable j, that is the partitioning position. So I should have one local variable, that is j. Yes. Then after calling partition, it should call quick sort once again from upon an array from low to j and quick sort from j plus 1 to high. See, actually it should be j minus 1. This is high. So actually this should be j minus 1, but I told you that jth position element, that is which is already sorted, acts as infinity for the first list, and this h, this is having infinity on the right hand side list. So that's all. This is a quick sort program. Let us call quick sort upon this list and see whether it sorts the elements. Quick sort, pass array, and the low is 0 here, high is 10, that is the last index is 10, total 11 elements I am having. Let us compile and run. Oops, this is int 32 max. Yes, that is 32-bit integer, int 32 underscore max. Yes, this was the error, so I have removed the error. Now you can see that the color also has changed because it's a predefined constant. Yes, the elements are sorted. 3, 5, 7, 9, 10, 11, 12, 13, 16, 24. So it has sorted the elements. Still it is giving a warning because, okay, variable n is not used. Yes, I am not using it. If you want, you can use this one, that is n minus 1, that is 10. Now it should not give any warning. Yes, warning is gone. Elements are sorted. So this is the function for quick sort. So you can try this. This is a simple program, though it looks like little difficult to the students, but it's very easy compared to the other programs, that is for trees and AVL trees, the lengthy programs we have seen. I have divided this into two functions, that is partition and quick sort. Here I wrote partition and next is quick sort. Even you can combine them and write it as a single function also. So it's up to you. So that's all in this video. In this video, I'll be talking about merging two lists, that is two arrays, and merging two lists in a single array. If they are in a single array, how to merge them, and merging multiple lists. So let us start with merging two lists, that is two arrays. See, merging is a process of combining two sorted lists into a single sorted list. If you observe, I have two arrays here, A and B, and the list of elements are sorted here and they are sorted here also. We want to combine these two and keep them in third array in the sorted order. Here I have, suppose, m elements, that are 5 elements, and here I have n elements, that are 4 elements. So These two lists may have same number of elements also or different number of elements also. So their sizes need not be same, they can be different also. And in each list, minimum one element must be there. We can merge these two lists by comparing their elements one by one and copying smaller elements in this third array. So for doing so, I will take I here and j here, that is starting indices, and k here. I'll merge few elements and show you. We compare a of I with b of j, which is smaller. A of I is smaller. So copy a of I here and then move I to the next element and also k to next element. Now one element is copied from here. Now again compare a of I with b of j. Now this time b of j is smaller. Copy that element 4. Now j will move to next element. Then k will also move to next element. In this way we will copy all the elements here. So I'll copy rest of the elements. See, similarly I have compared them and copied all the elements. So I got the elements in the sorted order. I was copying just the smaller element out of 2. Now I is on last element of A and here j is also on last element of B. Now if I compare these elements also, a of I with a of j, so this is 23 and 25. So 23 is smaller, 23 is written here. Then I moves to next index. So I becomes 5 and k also moves to next index. Now if you observe, one of the list has finished. All the elements in first list, that is A, has finished, and there is some remaining element in second list B. There is some remaining element. And definitely this is going to happen. One of the lists will finish and the other list will have at least one element remaining. So here in example there is one element remaining, or if I extend this list and add a few more elements to this, then there may be a few more elements. Now see, till 25 the comparison was done, remaining so many elements are there. So minimum one element will be there in one of the list. Either it may be left over in A or in B. So what I have to do is copy all those remaining elements in C directly. So I'll remove this. Now the remaining element in B, I have to copy it here. So 25 is copied here and K moves to next location, J also moves to next location. So both the lists are copied and merged together in third array, that is C. So this is the procedure. So let me write down the algorithm or the function for merging two lists. So let me write down the code here. Merge function is taking two arrays and the size of first array and the size of second array, m and n. Array C, assume that it's global, or else when we write the program we will decide where to keep it. Now let us start the process. So what we need I on this first list and j on this list, that is from starting index, k also on the starting index of C. So all three indices I, j, k are initialized with 0. They are at 0. Every time I should compare the element of a of I with b of j, whichever is smaller I should copy it in C of k, either a of I or b of j. So that code I will write down. If a of I is smaller than b of j, copy a of I element in C of k and increment both I and k. Otherwise, copy b element in array C and increment j as well as k. So this process has to continue. How long? Either A is finishing or B is finishing. Means I is less than m or j is less than n. So this is repeating process while. So continue this as long as I is less than m and j is less than n. If any one of them has finished, stop, come out of the loop. Now after coming out of the loop, like if we see the situation back again, this I had finished and j was still on the last element, right? So this may be last element or there may be more elements. So what we should do, copy all the remaining elements from B from the point wherever j is pointing, right? Don't again set it on 0. Wherever it's pointing, from there only copy all the elements from B to C. Or else same situation may be there in A also. So copy all the elements from A from wherever I is pointing. So I will write on that process for copying from A. So this for loop will copy all the remaining elements from array A if there are any elements remaining. If I is less than M, then this loop will continue. Copy all the elements from A of I to C of K, and K is incremented. And I am not initializing I, so let I start from the point wherever it is right now pointing. Then similarly, I should copy all the elements from B array also. If there are any remaining elements in B, that will be copied. See, this for loop will copy all the elements from array B to array C, remaining elements. Now don't confuse with this. See, any one of the for loop will execute. Both will not execute. If I has become equal to M, then this for loop will not execute. Then definitely J will be less than N, so this will execute. If I is still less than M, means B list has finished, remaining elements are there in A. Any one of these loop will run. Right? I don't have to check where the elements are remaining and all. Without that, I have just started the for loop from same point. So any one of the for loop will work. So that's all. This is the procedure for merging two arrays in a single array. Now about the time taken by this procedure, what we are doing, just copying the elements. How many elements? M elements from this side and N elements from this side. So the time is taken as M plus N. So it's a well known, it is like a notation that the time taken for merging is M plus N. Next we will see, is it possible to have more than one list in a single array? If so, then how to merge them? Yeah, here I have a single array of 8 elements. I have taken example. Now if you observe 2, 5, 8, 12, till here is one list. This is one list. Then 3, 6, 7, 10. This is second list. So two lists are there in a single array. One list is starting from index 0 to 3 and other one is from 4 to 7. So two lists in a single array, and I want to merge them, and after merging the result I want in A only. So yes, we can do this. So let us call this location as low and this location as high. So starting index low is 0 and ending index high is 7. And let us call this as mid. This is mid of these two. So that is 3. So first list is from low to mid and second list is from mid plus 1 to high. Two lists are there. Now for merging them, I need another array B of same size. Then if I perform the same procedure like comparing the elements of two lists, so for that I can take I here and J here and K here, compare the element of A of I with A of J and copy the element whichever is smaller. So the same process I can run what I was comparing, but this process was for two arrays. Now this is for a single array. So if I compare and copy, then first 2 is copied. Then 5 and 3 are compared. So 3 is smaller, 3 is copied. Then 5 and 6 are compared. So 5 is smaller. Then 8 and 6, so 6 is copied. 8 and 7, so 7 is copied. 8 and 10, so 8 is copied. Then 12 with a 10, so 10 is copied. Now when this list has finished, there is one remaining element 12 here. Copy this element. So the same process, assume this is array A, array B, but actually they are in the same array. So list 1, list 2, they are merged and we got the result in array B. So for merging, we definitely need extra array. We cannot merge and store the result there in A itself. It is not possible. So merging is not in place. We need extra space for merging. Now finally what I want is, I want to copy all these elements back again in A so that this sorted list is there in A. So yes, I can copy all these elements one by one and store this complete list in this array. So it becomes a single list of sorted elements. So that's all. We can have two sorted lists in a single array and we can merge them with the help of one auxiliary array and we can get back the result in A itself, that is single sorted list. How to do this process? So I will modify this one. So in this merge process, I need just array A. And the parameters I need are low, high and mid. So first is low, second one is mid, and the third one is high. 3 parameters are needed. And here I, J, K are perfect, but they should not be initialized to 0. Then I should be initialized with low and j should be initialized with mid plus 1. So I is initialized with low and j is initialized with mid plus 1. J should start from here. And k should not start from 0. It should start from low. We don't know where that low is. In our example, low is from 0. Low can be anywhere, any part of an array. So let us take k also on low. K is also on low. Now one more thing we need. We need an array to merge all those elements. So we need an array equal to the size of this list, whatever the size is. So let us create an auxiliary array B. So here I am creating an array B of size h plus 1 because high is till 7. So I need an array of size 8. So h plus 1, 7 plus 1, 8 I have given. Otherwise you can take one bigger size array, let us say 100. Instead of that h plus 1 you can take one large size array, if you don't bother about space. Now next, in this code also I have to make changes. I should be less than or equal to mid. So I should stop at mid. If it is going beyond mid, then the first list has finished. Then same way, j should be less than or equal to high. High. These are the changes. Then comparing the element a of I with a of j only. And this is b. This is array is b and copying a. And this is b. And this b of j is not there. This is a of j only. See, this portion is a of I and this portion is a of j. This is a of j only. Then this one, I less than equal to mid I should write. So this is less than or equal to mid. Copy these elements in array B. Then j less than or equal to high I should write less than or equal to high. And copy all the elements in B from A only. So the code is modified with some changes. And it works for single array now. Then one last thing is remaining. All these elements should be copied back to A. So here I will write on a loop for copying all the elements. For I takes values from low to high, copy element from B of I to A of I. So these elements will be copied back in A. So we get a final merge list in A. So this procedure is very useful, merging two lists from a single array. In sortings, that is merge sort, we will utilize this. So when I explain merge sort, I will not be explaining this. Merge means this procedure which takes parameter array A and low, mid and high. Now next, one more thing about merging, that is merging multiple lists. If you have more than two lists, then how we can merge them? Now merging multiple lists. I have taken an example of 4 sorted lists. And I want to merge them into a single sorted list. So what could be the procedure? So first procedure I am showing you. For preparing merge list E, let us call it as E. If there were two lists, we were comparing the elements of two lists, the smaller one we were writing. But now we have to compare first element of all these 4 lists and copy the smallest element here. So 2 is the smallest element that is copied. Now when this is copied, 2 is copied, let us exclude this and compare these 4 elements from these 4 lists, that is 5, 3, 5, 8. So 3 is smaller, 3 is copied here, then exclude this one. Now we have to compare these elements, so these 4 elements. So it means we are comparing one element from each list. So at a time we are comparing 4 elements, yes. And we are trying to merge all 4 lists together. Yes. So if we are doing this, then it is called as 4-way merging. This method is called as 4-way merging. So it means if there are 5 lists, then 5-way merging. If there are m lists, then it is m-way merging. So m-way merging is a known term. M-way merging means merging m sorted list into a single sorted list. So that m can be anything. It can be 3, it can be 4, it can be 10, it can be anything. So we are merging all lists together. So we compare one element from each list and copy the smallest one. Then there is another solution for this one. We look at that solution. Let us look at another method. First, we will merge these 2 lists and we get another list. So these names are A, B, C, D. So let us call this as E. We get another list E. Suppose these are merged. Suppose this is merged list of these two. Then we can merge these two again. So this is F and this is the result of this merging. Now instead of 4 I have 2 now. I selected 2 at a time, that is pair of list I have merged. Now I can merge these two together and prepare another final list. So this is the merged list of these two. So that in turn it is a merged list of these 4 lists. So instead of merging all 4 together, I can take a pair of any 2 lists and we can merge them. As we are selecting only 2 lists at a time, so this is called as two-way merging. Yes, two-way merging. So this is a two-way merging. See, instead of selecting these two AB, even I can select AC also. Or I can select AD or I can select BC. Any pair I can select. And one more thing. After selecting AB, instead of selecting CD, even I can select C with E and merge. Then again in that result I can merge D. So one by one you can merge them in the result. So any pattern you can follow, whatever the pattern suitable, you can follow that pattern. So that's all about 4-way merging, M-way merging or 2-way merging. Now in next videos we will be looking at merge sort, and merge sort uses 2-way merging. We will look at iterative version of merge sort as well as recursive version of merge sort. Now the topic is iterative version of merge sort. This is 2-way merge sort. 2-way merge sort can be implemented iteratively also, recursively also. So first we will learn iterative version. So for explaining merge sort, I have already taken an example array. So let us see the problem. I have an array containing list of 8 elements. One list of 8 elements and we have to sort them. I'll repeat the problem statement. There is an array containing one list of 8 elements, we have to sort it. Now to apply merge sort, we change the statement. We say that there is an array containing 8 lists. 8 lists. How? See, this 8 itself is one list. 3 is one list. 7 is another list. 4 is another list. 9 is another list. 2 is. So like this we say that each element is a list. So now I'll repeat the statement. There is an array containing 8 lists where each list contains one element. Problem statement is changed. Now you tell me, if a list is having just one element, is it sorted or not? Yes. If you take just this element as one list, it is sorted. This element as a list, it is sorted. 7 sorted, 4 sorted. So each list is sorted. So when they are sorted, we can directly merge them, and merging gives sorted result. Yes. So now the task is we have to merge 8 lists. So how to merge 8 lists? So two-way merging means we'll pick up 2 lists at a time and merge them. So let us start. So first we will merge these 2 lists. This list is having one element 8, this list is having one element 3. So we will merge these 2 lists and make it as a single list. So result will be 3 is smaller, 8 is greater. So we get 2 elements and this is new merged list. So this is sorted. Then we select next pair of list. So we have 2 lists now. One is having 7, one is having 4. Merge these 2. Result is 4, 7. Because 4 is smaller. Now this is sorted. Then we select next pair. 9 and 2, when you merge, it will become 2 and 9. Because 2 is smaller, 2 comes first. Now we'll merge this pair of list. So 5 is smaller, 5 comes first, then 6. So this is merged. So we got 4 lists now. Out of 8 lists, when we have merged 4 pairs, then we got 4 lists. Now if you observe, earlier, what was the size of list? Just one element. Now, what is the size of list? 2 elements each. 2 elements each. Now, again, we have to continue. We have to continue merging. Now, again, go through this entire array by merging lists. So, what are those lists? Merge these 2 lists of 2 elements each. The result will be smallest number is 3, then 4, then 7 and 8. We got one list of 8 elements. Then merge these two lists. 2 is smallest, then 5, then 6, then 9. So we got another list. Now 4 lists we have merged by taking pair at a time. So we got 2 lists. Now we have to merge these. Size was 1 element, size was 2 element, now size is 4 element. So size is getting multiplied by 2. Size of the list is growing by 2. Now we have to merge these two. Merge these two. 2 is smaller, then 3 is next, then 4 is next, then 5 is smaller. Then compare these two, so 6 comes next. Then compare these two, 7 comes next. Then 8 comes, then 9. That's all. This is sorted. So this is how iterative version works. For 8 elements, how many passes we have performed? So pass means we have gone through the entire list at once. So this we have gone through and we got this result. So this is first pass. Result of first pass. Then this is the result of second pass. Then this is the result of third pass. So we have performed only 3 passes and we got the result. So total how many elements were there? Total 8 elements were there. So for that we have performed 3 passes. In this pass we were merging one element. So we were merging 2 lists. So the size was 2. Then next time it was 2 elements. So together the size was 4. The next time 4 elements. So together the size was 8. So let us do analysis. See, this is an iterative version and it is having passes. Passes means we are going through the entire list at once, not partially. At once we are going through it. If it is recursive, it will not have passes. It is iterative, so that's why it's having passes. So in one pass, how many elements are merged? So in one pass, what is the work done? We are doing nothing but merging the elements. So total how many elements are merged? N elements are merged. Then again from this, how many elements are merged here? From there to here, N elements are merged. Then again from there to here, how many elements are merged? N elements are merged. So this is done how many times? So if you turn this upside down, you can see it as a tree. See, this is the root, left child, right child, and its left child, right child, and these are left and right child of this one, and these are the left and right child of these nodes. So it looks like a tree. So it is same as height of a tree. So height of a tree is nothing but log n. So this is done for how many times? Log n times. Or else there are total 8 elements. 8. Log 8 base 2 is how much? 3. So it is done for 3 times. 3 passes are required. So that's how it is log n. So total time is n, that is done for log n times. So the time complexity is order of n log n. So the time complexity of iterative version of a two-way merge sort is n log n. Now let us look at algorithm or a function for iterative version of merge sort. So I will write on the function, then I will explain you. So here is a iterative version of merge sort. It is taking array as a parameter and n, that is number of elements. So here number of elements are 8. So this is 8. Then this for loop is for passes. So how many passes we need for 8 elements? 3 passes. That is log n passes. So here I have taken p assigned 2 and the p is getting multiplied by 2 and reach up to n. So if I write p values, first time p will be 2, then the p is getting multiplied by 2. So next time p becomes 4, then again multiplied by 2, so p becomes 8, and it will continue as long as it is less than equal to n. So now it is equal to n, so it will continue. So total 3 passes it will perform. P will take 3 values. So when the first pass is performed on the original list, p value will be 2. The next pass, p value will be 4. The next pass, p value will be 8. So what is this? I will explain you. If I take from the last list, p value is 8 means total 8 elements are merged. In this 2 lists are there. One is with 4 elements, the other one is also with 4 elements. So total 8 elements are merged. That's why p value is 8. If you remember merge function or algorithm that we have seen in the previous video, it takes low, mid and high of a single array and merge them with the help of auxiliary array. If you have not seen previous video, just watch previous video upon merging. There I have explained you how two lists in the same array can be merged. So for that, low, mid and high, three values are required. So when P is 8, low should be this one and this should be mid and this should be high. So it will merge a list from low to mid and second list is from mid plus 1 to high. So that's how for 8 it works perfectly within a span. This is mid. Now when this is 4, so this is low, this is mid and this is high. So just two lists are merged. Again it has to be continued for this one. For this one also it should be continued. Again this is low, this is mid and this is high, where the total elements are 4. So similarly, when P is 2, then more than one pair of list has to be merged. So for that I have taken one more for loop I. So I is taking a span of two list, then again two list, right? So it is moving by P, see, moving by P. So using I we calculate low, high and mid. So as we have to merge more than one pair of list, so for that we have this iteration I. So if I show it on first list, first time I is here, so these two elements are merged. Next time I will be here, then these two elements will be merged. Next time I will be here, then these two elements will be merged. Next I will be here and these two elements will be merged. And each time this is low, this is high and this is mid. This is low and this is high and this will be mid. This is low and this is high and this will be mid. So that's how all our calculated and merged function is called. So if you want to understand it by taking values, then you have to substitute, then you have to prepare a table and understand how these values are changing. Then one last thing in this function. I have taken exactly 8 elements. So log 8 base 2 is 3. So I get exact answer. If these are not 8 elements, so if suppose this is 9, then one extra element will be there. Suppose I will take one more element 1 here. That will not be paired with anyone, it is not merged. Then same 1 carry on here. Again this 2, this is left over. Then again 1 carried on here. So this 2 will be merged. Then again 1 is left over. Then it comes as it is. Then this list should be merged with this one. So one more pass has to be performed. So for that, this merge is there. So when you have odd number of elements in a list or the list size is not in powers of 2, then some elements will be left over. So for merging them, this function is there. So that's all about iterative version of merge sort, which takes n log n time. I will write the program and run it and show you. In this video, we will write a program for iterative version of merge sort, that is using loop. So already we have used a project called sorting and we have written all the sorting procedures inside the same project. So in the same project, I will write on the functions for merge sort. So for merging, already we have seen that we have to write a function for merge separately. So first of all, I will write a function for merge, that is merging two lists from a single array. So it needs 3 parameters, that is low, mid and high. These are the 3 indexes and the first parameter is the array. Then I need the variables like I, j and k, and also we need a array b, that is auxiliary array b of some size. So instead of deciding how much size I need and all, I will take some maximum size temporarily. So if at all you want to decide the size, then you can take the size. If at all you want to judge what the size required, then you can declare the array of required size. Now here, just to make it easy and simple, I have made it 100 size. Now we have to run a while loop, that is that is comparing and copying the elements while I is less than or equal to mid and j is less than or equal to high. And every time we should check the elements, that is if a of I, if it is less than a of j, then in b of k plus plus we should copy an element from a of I plus plus. Otherwise, in B of K plus plus, we should copy the element from A of J plus plus. This process should continue as long as the elements are available to compare. And once one of the list ends, we should stop and copy the remaining elements either from the first list. So if I is not less than equal to mid, it should continue and copy the elements. So in B of K plus plus, it should copy the elements from A of I. And same way, if there are remaining elements in the second list, that is j is less than high equal to high and j plus plus, it should copy the elements in B of K plus plus from A of j. And after copying all the remaining elements, we should transfer all the elements from low to high, from array B to A back again. So I is less than equal to high and I plus plus. So every time A of I is copied with B of I. This is for transferring the elements. So this function already we have discussed, we have seen it. So the same function I have written. Then here I will write on a function for merge sort, that is I merge sort, iterative merge sort. Then it should take the parameters, that is array of elements and the number of elements n. Then inside this we need few variables like I, p and low, high and mid. Then first for loop is for passes, p, that is first pass, that is the gap in between the elements, that is the list size will be 2, and we will continue while p is less than equal to n, and p will be moving by p into 2, so always the list size will be getting double. Then for inner for loop, this is for merging all the list in a single pass. So I should start from 0, I is I plus p minus 1 is less than n, this already we have discussed. Then I should be incremented by I plus p. Then here we will find out low, that is I, and high, that is I plus p minus 1. And then we will find out mid, that is the floor value. So floor value, anyway these are integers, so we will directly get floor value low plus high divided by 2. So we got low, mid and high. Then we will call merge function, which we have already written there, that is array and the low and the mid value and high value. That's it. So this for loop will perform one pass and it will merge all those small list of size 2 each. Then it will become 4 elements each and goes on. Then at last I should see that if p by 2 is less than n, means if there are some more elements remaining, then we should merge array of elements starting from 0 and p by 2 comma n minus 1. That's all. So this all we have discussed and I have explained you. I have written the code, the same code I am writing here. Now let us call merge sort, that is I merge sort, from the main function. Oops, it did not show the list properly, it has not sorted. There are some warnings. Okay, let us check what is the error, what is the problem. Oh, I, J, K, they are not initialized. Oh yes, I have not initialized them. I should be L and J should be mid plus 1 onwards and K should also be L. Now they are initialized. Let us run. Let us check the elements. They are sorted. Yes, 3, sorry. Oh, 3 is missing here. 3 is at the last. So it means 3 is not included in the list. So there is one more problem in this one. So why 3 is not included? Let us check. P by 2 minus 1. Yes. See, we are having indices starting from 0 onwards. So if there are 8 elements means 0 to 7. So it should be -1. P by 2 may be 8, but -1 I should take. Let us run now. Yes, perfect. So it has sorted all the elements. So that's all. This is an iterative version of merge sort. Anyway, merge sort is a two-way merge sort only, but because this is iterative and one is recursive, so this one is called as two-way merge sort. The next we'll be looking at recursive merge sort, and also we will see the program for that one. Now we will look at recursive version of merge sort. It is a two-way merge sort and it follows top-down approach as it is recursive. So let us look at the problem and observe a few things. See, a single array of size 8 is given and the elements are not sorted. Let us check half of this array. Are these 4 sorted? No. So these are also not sorted. Then let us look at half of this half. Whether these two elements are sorted? No, even these are not sorted. Then let us look at half of this half. So just 2 elements. So I will try to mark it. First half, this side, is it sorted? No. Next, this half, is it sorted? This part? No. Let us take the half of this one. Now are they sorted? Yes, when you have reduced down to one element, then obviously they are sorted. So in two-way merging, we need 2 sorted lists so that we can merge them and make a single sorted list. So when I have partitioned this one, there is no guarantee that left side and right side are sorted because the array is not sorted. Then I have taken the left hand side and again splitted it into half. Then again there is no guarantee that these two are sorted. Then on this one also again I have taken half. Now there is a guarantee that these two are sorted because those are single elements. So yes, this is the idea in merge sort. As merge sort is a recursive procedure, when a single large array is given to it, then it will break it into 2 halves. And there is no guarantee that these two are sorted. Then again break this into half until it reaches one element. Now one element means they are sorted. Then from there it will start merging the elements. It will start merging those smaller list and into a larger list in the returning phase of recursion. So first I will write down the algorithm, then I will show you the working, how it works. So this is a merge sort, an array and lower index and higher index are given. Suppose this is an array, this is low and this is high. So low is 0, high is 7. So this A, low and high, 3 parameters are given to that merge sort. Then as a complete list is given, complete array is given, a big array is given, which we have to sort through merging. So then it should be broken into halves and merged together. So it will divide the list into 2 and merge them together. So if there are more than one elements, if there is only single element, nothing to do. So low should be less than high. So at least 2 elements should be there, then only low will be less than high. If low is less than high, find out mid. That mid is low plus high divided by 2 and we need floor value here. So floor means if it is integer division, then we get floor value only. So this mid is this one. So low plus high by 2 means 0 plus 7 by 2 is 3. So this is mid. So first it will divide the list into half. Then this part should be merged with this part. But merging should be done only if these two are sorted. So let us sort this first and sort this one also. How to sort this? Recursively using merge sort only. So first it will sort these two sides, left side and right side. Once they are sorted, then it will merge them. So perform merge sort from low to mid. Perform merge sort on left side, that is on array, from low to mid, from low to mid. Then perform merge sort on right hand side also, that is mid plus 1 to high. Perform merge sort on an array on the right hand side, that is mid plus 1 to high. So it will sort left hand side and right hand side recursively. Then when these two are sorted, it has to merge them. So merge two lists. Assume that these are sorted, this is also sorted. We have to merge these two lists. See how many lists in a single array? Two lists in a single array. One is from low to mid, second one is mid plus 1 to high. Two lists in a single array, right? Single array. So already we have seen how to merge two lists in a single array with the help of auxiliary array B and again getting the result back in A. We have already seen that. So we'll call that merge process. This is merge array A. First index is low, then the middle value and also high. Three indices. We have already seen this merge. That's all. This procedure is recursive. End of the procedure. This is so small, but this is recursion. So this will expand like anything and sort any large list. So let us trace this merge sort on this example. If we call that merge sort on this array, low is 0, high is 7. So first call is 0, 7. 0, 7. I am showing only low and high. Array is always there. Then what it will do? Find out mid. So what is the mid value of this one? 0 plus 7 by 2 is 3. Then it will split the list at index 3. So from here the list is split. 3 is mid. So this is mid. Then call merge sort on left hand side. So first one, that is A low to mid. So it will call itself on left hand side. That is from 0 to 3. This is the first call. So second call afterwards, once this has finished, then it will go to second call. I will mark these steps 1, 2, 3, 4. See, first find out middle, okay. Then go on the left hand side. This is on the left hand side list. Right hand side and then merging is remaining for this portion, right? For this call, two steps are remaining. So let us continue with the left hand side. This is 0 to 3. So low is 0 and high is 3. So now high for this list is till here only. Then find out mid. 0 plus 3 by 2 is 1. So mid will be 1. Then the list is again divided into 2. So mid is found out, then list is divided into 2. So first the left hand side, that is low to mid. So again a call is made from low to mid, that is 0 to 1. 0 to 1. Then this is a fresh call, 0 to 1. Low is 0 and high is 1. Low is less than high, yes. 0 is less than 1, yes. Then find out mid. What is the mid for this one? 0 plus 1 divided by 2 is 0 only. So mid is 0. So now low is 0, high is 1 and mid is 0. This is mid itself. This is mid. Then after finding mid, call upon left side first. Then on the left hand side it will call itself, that is low to mid. Low to mid. Low is also 0, mid is also 0. So 0, 0, it is called upon this one. See, so many calls are made. Now at this stage, when both are 0, 0, low is not less than high, it will not enter inside. It will not enter inside. So this call terminates here. So it goes back to the previous call where low was 0, high was 1. Low was 0, high was 1. Right? Mid was 0. On these two steps it has to perform. Let us go on the right hand side. So first go on the right hand side. That is mid plus 1 to high. That is 0 plus 1, 1. High is 1, 1. Again, these are equal. So this is a single element. So it will not perform anything. So right now actually the list is splitted, right? So first 0 element this side, 1 element this side. So in all till here, what was happening was a list of some elements are given. So it is divided. Again it is divided. Again it is divided until it becomes 1 element each. Yes, 1 element each. Now for this call, left hand side is finished, right hand side is finished. Now last statement, that is merging, has to be done. So calculating mid, left side, right side completed. Now merging has to be done. So merging has to be done. So the element is 0, 0 with 1, 1. This is one list, this is second list. Two lists are merged. So now the new result is 2, 8. And this is sorted. This becomes one single list. First 2, then 8. Then this is finished. This was the first merging. Now it will go back to previous call because this portion is finished. Then it has to take the right side. So on right side is mid plus 1 to high. Mid plus 1 to high. So this is 2 comma 3. So it will go this side. Low is 2 and high is 3. Find out mid. 2 plus 3, 5 by 2 is 2 only. So mid is 2. Mid is 2. So list is divided into 2 halves. Yes, on the left hand side low to mid. Left hand side low to mid. That is 2 to 2. Single element, nothing is done. Right hand side mid plus 1 to high. That is a 3 to 3. Right hand side 3 comma 3. So here also nothing will happen. It terminates. Now left side completed, right side completed. Left side completed, right side completed. Merge. So these two elements are merged. So 2 and 3 are merged together. Like these were merged together. Now these two will be merged. Now which is smaller? 6 then 9. So you can see that actually two lists are getting merged and each list is having just one element. So this was the second merge we performed. Now coming back to this one. Now for this side, left hand side is completed, right hand side is completed. This is remaining. So on this left hand side completed, right hand side completed, merging is remaining. So upon this merging will be done. So for this list, what is low and high? Low is 0, high is 3 and mid is 1. Mid is 1. So first list is from 0 to 1, 0 to 1. Second list is from 2 to 3, so 2 to 3. So these two lists with the two elements each, they are merged together and the result is 2, 6, 8, 9. This is a single list. So this is the third merge and finally it will have total 4 elements. So you can see that it has called upon left side, called upon right side, then it will merge. It is working recursively. Now remaining from this side, I have to complete it. So without explaining, I will simply fill the values and quickly I will show them. For this call, right hand side is called, right hand side is mid plus 1 to high. So this is 4 to 7. Low is 4, high is 7. Then find out mid. 4 plus 7, 11 by 2, that is 5. Mid is 5. So this is mid. And list is splitted. Then call upon left hand side. So left hand side is 4 to 5. Low is 4, high is 5. Find out mid. Mid is 4 again. Mid is 4. Then call upon left hand side 4 comma 4. This is single element, nothing will happen. Call upon right hand side 5 comma 5, single element, nothing will happen. Go back and this is fourth merging. So merging of 4 comma 5. These two elements are merged together. So this will be 3, 5 and this is sorted. Then go on the right hand side of this one. Right hand side is 5 plus 1, that is mid plus 1, 6 comma 7. Then mid here is 6. Then left hand side is 6 comma 6. There is single element, nothing will happen. Right now it is working on this low and high 6 and 7 and mid is 6 only, right? Then right hand side 7 comma 7. This is single element. Then go back and perform last step, that is merge, fifth merge. So what is that? These two are merged together, then 7 and 4. So 4 is smaller, 7 is greater. So this becomes a single list. So this is single list of 2 elements, single list of 2 elements, single list of 2 and single list of 2. This 2 are finished. So go back. Then this is sixth merge. So 4 to 7 elements are merged, 4 to 7. So that time low was here and high was here and this was mid. So 4, 5 and 6, 7. These two are merged together. So this becomes 3, 4, 5 and 7. These two lists are merged. This becomes one list. Now for this main list, left hand side finished, right hand side finished. Now you can see that both these two sides are sorted recursively using merge sort only. Now upon this 0 to 7 where low is on 0, high is on 7 and mid is on 3. So for this one merging will be done. So one list is from here to here, which is sorted now in this shape, and this is from 4 to 7, this is sorted, that is in this shape, right? Now the elements are no more like this, they have changed to this one. Now merge these two by using this merge, low to mid, mid plus 1 to high. Then these two lists are merged together. So this is 2, 3, 4, 5, 6, 7, 8, 9. And this is final merge. This was seventh merge. So the procedure was recursive. So I have traced it and I have shown you and also form a tracing tree. The way we write is just 4 statements, but how it works, it's very huge and it depends on the size of a list. Now let us do analysis of merge sort. So instead of looking at the code, let us look at this tracing tree. So what the work we are doing? We are doing nothing but merging. So merging of how many elements? See, if I look at this root, 4 elements from here, 4 elements from here are merged and we got total 8 elements, that is n elements. So the result obtained here is n elements are merged. Then we are getting the result by merging these two here, So total how many here? 4. Then here also total at this level, if you see, at this level, total 8 elements are merged, that is n elements. And at this level also n elements are merged. And last level nothing is done because those are representing single elements. So how many times merging is done? N, 3 times. So that is equal to what? Depends on the height of this tree. And height of this, and this tree looks like a full binary tree. Yes, it is like a full binary tree or complete binary tree. So the height is how much? Log n. So this is done for how many times? Log n times. So merging is done for log n times. So n is the time taken for merging and it is happening for log n time. So the time complexity is order of n log n. Yes, the time complexity is n log n. So the time complexity of merge sort is n log n. And there is no best case or worst case. So this is average case time. So this was the time analysis. Now more I have to discuss. Just let me show you one more thing. See how the merging was done. If this is a tree, then first this was merged, then this one, then this one. So left, right, then root, left, right, then root, then left, right, then root. So yes, merging is done in post order. So if you see this, recursive call, then merge. So merging is written after 2 calls. So it is post order. So in the post order, the merging is done. So if you represent this in the form of a tree, so in the post order of a tree, merging is done. Now let us come to the space complexity of merge sort. In this merge sort algorithm, the space that we require is A. So that is of size n depending on the number of elements. But if you see this merge algorithm, that uses auxiliary array B for copying the merge result. So that should also be of size n. Then as this merge sort is recursive and the recursion utilizes a stack, so what should be the size of the stack? Depending on the height of this tree. So size of the stack is log n. So the main 2 things that we have to highlight here, that as it is recursive, it uses stack. That is the first point. Second thing is it needs extra array. Extra array is compulsory for merge sort. So total space required is 2n plus log n. And in this, n plus log n is the extra space required for merge sort. So in comparison based sorting, merge sort is the only algorithm which requires extra space. Otherwise we saw insertion sort, bubble sort, heap sort, quick sort, none of them uses extra space. Merge sort uses extra space in comparison based sorting. So that's all about merge sort algorithm. In this video, we will write a function for recursive merge sort. This project is a sorting project. All the sorting functions I am writing in the same project. So right from the bubble sort till merge sort, we have same project. So if I scroll up, you can see that already I have a function for merging 2 lists from a single array. As our recursive merge sort utilizes this function, so we'll be directly using this one. We don't have to write the function once again. And this was the iterative merge sort we already wrote. Now here above the main function, I will write on recursive merge sort. So let us call it as merge sort, and it should take an array of elements and low and high. Then if there are more than one elements, then it should sort them. If low is less than high, then it should sort them. So first of all, it should find out mid. So for that, I will declare a variable that is mid. And here inside, I will find out mid. Mid equals low plus high divided by 2. This should be inside the brackets. Then perform merge sort upon an array from low to mid, and perform merge sort from upon an array from mid plus 1 to high. Then perform merge upon an array from low to mid and mid plus 1 to high. So just mention high. That's all. A very small program, 4-5 line program. So it's a recursive function. Now let us call this function from main function by passing this array of elements, and low is 0 and there are total 10 elements. Last index is 9. Let us run this. Yes, the elements are sorted. Yes, total 10 elements and all of them are sorted. And here I am getting a warning that I have not used n. So yes, I wrote 9 directly. Instead of that, I can say n minus 1. If I run again, the warning is gone. So that's all in this merge sort. You can practice this function, write on the function by yourself after watching this video, or you can pause this video and you can type the program simultaneously. The topic is count sort. This is index-based sorting. This is one of the easiest sorting to understand, and also it is fastest, but it consumes a lot of memory. Let us see how it works. I have a list of elements in an array A. These are the elements that I want to sort them. So for sorting these elements, I have taken an array. Array name is count. And the size of this array should be equal to the largest element that we have in this array. See, the largest element in this array is, this is 15. 15 is largest. So I have an array of size 16 so that I have index 15 also available in this count array. So this is the requirement. The second requirement is I must initialize this array with some empty values. So there is nothing like empty. So we can take 0 as empty or minus 1 as empty. So I will take 0 as empty. I will initialize with zeros. So let us initialize this array with zeros. So the count array is ready with 0. Now we are ready with the setup. For sorting this list, I have taken an array equal to the maximum size element, and also I have initialized it. Now let us start the process. So the process is scan through all these elements in this array one by one. So if I go upon the first element 6, so whatever the element is at the same index in a count array, increment the value. So make it as 1. Then go to next element 3. So go to index 3 here and mark it as 1. What does it mean? This says that number 3 is present there in that array. So far we found one occurrence. Yes, continue. Next element 9. So mark this as 1. So there is one 9 available there. 10. Mark this as 1. Then 15. So mark this as 1. That is increment it. The next is 6. Go to 6. Already 1 is there. So increment it. So we get 2. Then 8. Go to index 8 and increment it. So it is 1. Then 12. Go to index 12 and increment. 3. Go to index 3. It's already 1. So increment it to 2. The next 6. Go to index 6 and increment this one. So we have 3. So in the count array, actually I got the number of occurrences of each number present in an array. So the largest number present was 15. So I must have index 15 also here. Right? If there is largest number is 100, then this array size should be 100. So how many times each digit is appearing there? For that corresponding index, we have written its occurrences. So this is one step of a process. Now we want sorted elements. So assume that these elements are removed. So I'll remove them. So I have cleared this one. Now the next step is I should copy all the elements from count array back to actual array A. Let us do it. So the procedure is scan through this count array, and if the value is more than 0, greater than 0, then write down the index as a number. So let us see. This is 0, move to next, 0, move to next, 0, move to next. 3 is there. 3 is having 2, means 3 is 2 times. So write 3 2 times. So this I can write it one by one also. First write 3, then decrement it. Then again write 3, then decrement it. It becomes 0. So this is completed. Now move to next. This already 0. This move to next already 0. This 6 is 3 times. So write 6 one time, decrement it. Write 6 one more time and decrement it. Write 6 one more time, then decrement it. This is completed. Go to next, go to next. This is 8 is 1. So write 1, 8 and make it 0. 9 is 1 time. So write 9 and make it 0. 10 is 1 time. So write 10 and make it 0. 11 is 0 time. 12 is 1 time. So write 12 and make it 0. Then 0, 0. This is also 1 time. So write 15 and make this as 0. So that's all. We got the elements in the sorted order. See here, intentionally I have taken duplicate elements so that you can understand what is the meaning of count. If there is only one copy of an element, then each place we would have got just one. So if there are duplicates, we will have the count of that duplicates. How many duplicate elements are there? So that's all. The procedure is simple. Now analysis. What is the time taken by this procedure? What we are doing in the procedure? Scanning through array A. How many elements it's having? N elements. Then again scanning through array count. How many elements are there? N elements are there. Let the size be n. Or if the sizes are different also, doesn't matter. We say n means sum, right? Some elements. So time is n plus n. So we can say order of n. If you say no, this size is n and this size is m. So okay, it is m plus n. M plus n can also be written as order of n. But when you use m plus n, then this gives the idea that merging is used here. So it's not merging. So better call it as n. So this is linear time taking algorithm. Then what about the space? It needs a big size space, that is array, depending on the maximum number that you have in original list. So space consumed is huge. That depends on the maximum number. So it takes a lot of space. So we can say extra space is also n only, but it is larger space. So this is space consuming algorithm. So unless we have the range of numbers in small range, we cannot think of using count sort. If the range is very big, then we need a big size array. Now let me write down algorithm or a function for count sort. I have a function here, that is count sort, taking an array and the number of elements, the size of this list. Size of this list is 10. So n is 10. Now next, what I need in that count sort algorithm is I need an array called count. So what should be the size? Equal to the maximum element present in this array. So max assign find max. So let us write one function to find out the maximum element in an array, where it takes array A as a parameter and the size of an array. Find out maximum, and we know the max now. Like in our example, it was 15. So for this I should declare a variable. So I will also declare a variable. I may require more variables, I'll declare them. Now based on this size, I need an array. So let us create it dynamically. So for that I will take an array with the name C. I'll just change the name to C instead of count, lengthy name. I'll just say C. So let us have one pointer of integer type C. So C assign new int of max size, max. See, from this max I will get 15. But the array size should be 16 because it starts from 0 onwards, 0 to 15. So max plus 1 array size. So this is an array created. Next, I have to initialize this array with 0. So with for loop, I can initialize this with all zeros. So this C array I will initialize. Now with for loop, 0 to max plus 1, C of I assign 0. So all these locations I have initialized them with 0. Now next I have to scan through this array, and for every number, whatever the number present here in A of I, at the same index I should increment the value. So that work I can do it by scanning through this array A using for loop. So I will write down the code here. Say this for loop is going from 0 to n, that is from 0 to n for this size array. Then for every element, that should become the index of count array. So if it is a 3 means go to index 3, C of 3, right? If this is 3, then C of 3. So that element should become index of C array, and there I am incrementing 1. So this for loop will finish the task of counting all the elements. So just now we saw that the count array was filled. So I will write down the values once again. So I have written the values. See, these values will be filled with this for loop. Now the next step is, based on these counts, I should fill up the elements in array A. So element should be copied and it should be decremented. And if it is 0, I should move ahead. So for that, again I will write a loop. Now this time I will use a while loop, and I will write down the code for copying all these elements. So let us start I from here. See, this while loop, I starts from 0, I reaches up to max plus 1. That is 0 to 15. At 16 it will stop. And also I need a index pointer here on array A to copy the element. So I here and J here. So I will take one more counter there. That is J is also initialized to 0. Now I have to copy all these elements depending on the count, and I should fill the array A. So if this value, C of I value, if it is 0, then I should simply move I. Move I, move I. Suppose it is not 0, then I should copy this value 3 there and decrement this to 1 and move J, but don't move I. So if it is greater than 0, don't move I. If it is 0, then move I. So this I will do it inside the loop. So let me write down the code. See here, if C of I value is greater than 0, then in A of J, copy the value I. Means if I is a 3, then I should copy 3 there and decrement this value. So C of I minus minus. Otherwise, if this is 0, if you have copied both, this is 0 now, move I to the next. So else move I to the next. So with this for loop, depending on the count, the elements will be filled in array A. So let us look at the code once again. Find the maximum element from this array. Create a count array of that size. Initialize count array with all zeros. For this, count the number of elements present there and write the count here, increase the count. Then in this loop, copy all the elements from this count array back to A. So from the code, if you want to find out the time complexity, this for loop is n, and this for loop is also n, and this for loop is also n. So total it is 3n. Why it is coming 3n? Because initialization part also is included. So it is order of n. See here I wrote n plus n. Initialization I did not consider. So we got 2n, but now we got 3n because initialization also included. So whatever it is, 2n or 3n doesn't make difference. Finally, we want the degree of a polynomial, that is n. So the time taken by this algorithm is order of n. So that's all about count sort. In this video, we will write a count sort function. So already I have a main function and a list of elements available. Now here I will write down a function for count sort. Count sort, it takes an array of elements as well as the number of elements. Now here inside this I need few variables I, j and max for finding the maximum element, and also counting the elements I need a count array, so for that I'll take a pointer. Now the first thing is I should find out the maximum element in the list. So for that I will write a function to find max. I'll pass an array and the number of elements n. So let us write down the function here. For finding a maximum element, I should have a minimum element. So int 32 underscore min, this will be a minimum element, integer element. Then I need I for scanning through this list. So for I, assign 0, I is less than n, and I plus plus, if any element from an array is greater than max, then we will change max to that element. So already we have the smallest element, so we can find out maximum element, return max. So this function will find out the maximum element from a array. Now here inside count sort we will create an array of that size. So C assign integer type array malloc function, and this should be size of integer, and this should be multiplied by max plus 1, as we need an index up to that number, that is maximum number, because the indices start from 0, so we should take one extra. Like if you want 10th index, then you should take size of array as 11, so you get indices from 0 to 10. Then this array should be initialized, so I assign 0, I is less than n, sorry, max plus 1, and I plus plus. So the C array should be initialized with 0. All the elements are initialized. Count is initialized to 0. Now we have to scan through this array, that is A, that is being passed. So we will scan through this one for I assign 0, I is less than n for n elements, I plus plus, and wherever the element is found, so in C of A of I, we will do plus plus increment if the element is found. Then we have to scan through both the arrays I, that is A and C. So I assign 0 and J also assigns 0. Now while J is less than max plus 1 till the end of the C array, we will check if C of J is greater than 0, means it is not 0, means there are definitely some element. So at A of I, we will copy that J element, and also we will decrement the count of that J. So J minus minus. So I have used I for our array A and J for this C. Okay. So the variable names. And if J is greater than 0, we will do this. Otherwise, we will increment J. So J plus plus. And that's all. This will sort the array A. So from here, I will call count sort function by passing array A, and the number of elements are n. Yes. Let us run the program and check. Oops, we got an error. Let us see what is the reason of this error. C is null. C is null. And this A is having element 11. Okay, perfect. Then this is 0 and this is null. It is giving null. Okay, so it means C is not assigned any array. We are creating an array. So let us see what the problem is there in that array creation process. Okay, malloc we have not included, it's a warning, so it will implicitly declare, so we need not go there and write on stdlib. Max plus 1, they should be inside bracket. Then what is the value in max? Oh, some large value. So, okay, yes, I have written a function for finding max, but I did not call that function. Yes, I missed that statement. So find max, I should send an array and the number of elements n. So max I found out. Let us check the code once again before executing it. This is initializing an array and this is called incrementing all the values. Then I is for array A, J is for that is count array, and when element is count value is greater than 0, then copy the element in name of I. Oh, I plus plus also I should do, that is J element is copied and C of J is reduced, so that it becomes 0 and we continue upon the next element. Yes, everything is perfect. Yeah, I plus plus here, it was missing. That's all. Let us run this now. Yes, perfect. 3, 5, 7, 9, 10, 11, 12, 13, 16 and 24. So it's working perfectly. So this is the count sort procedure. So this is a faster sorting algorithm that takes order of n time, but it takes a lot of space. That's all in this video. Now our next topic is Radix Sort. So for sorting the elements using this method, already I have taken an array of elements. These are the array of elements that I am going to sort them. This sorting method is same as bin sort, similar to bin sort. But in bin sort, we were taking array of bins equal to the largest element present in the array, right? So what is the largest element in this one? Yeah, here, 348. So imagine I should have an array of bins of size 348. It will require a lot of space, a very big size array. So to make that a bin sort simple, we introduce Radix Sort. So how it is different? See, we will not take 348 bins, but we will take only 10 bins. Why only 10 bins? What these numbers are? Integer numbers. Okay, integer. But which number system? Decimal number system. Okay, decimal number system will have how many digits? 0 to 9. So take 0 to 9 bins. That's it. These are enough for sorting those elements using Radix Sort. So that's why the name is Radix. It means if these integers were in a binary form, then how many bins enough? 2 bins enough. Yes. If suppose this is octal numbers, these are all octal numbers. Suppose if they are octal, then only 8 bins are enough, 0 to 7. So that's why the name comes Radix Sort. So for sorting this decimal numbers, I have already taken 10 bins and also initialize them to null. So setup is ready. Next we have to learn how to sort them. So let us start sorting the numbers. So let us start the procedure. In the procedure, I will scan through this list of elements and every element, example 237. For 237, there is no bin available here. No, you don't have to drop it in bin 237. You have to drop it in bin 7. So it means I should just check last digit of a number. Yes, just check last digit and drop it in that corresponding bin. So this is 237 will get dropped here in the bin 7. So I will not draw nodes and all. I will just write number 237. It is dropped here. So how I can know that last digit? So whatever the number is, if it is a of I, then mod it by 10. You get the number. So last digit you will get. Yes. Now same thing I will do it for all. 146, this is 6. It will go into bin 6. 146. The next is 259. It will go to bin 9. 259. Next is 348, bin 8. 152, bin 2. 163, bin 3. 235, bin 5. 48, bin 8. Already number is there. So, okay, below that, 48. 36, bin 6. Already number is there. So, below that, 36. So, 62 is here in bin 2. So all the numbers I have scanned and I have filled them in their corresponding bins based on the last digit. Are they sorted? Let us see. I have to take out all these elements from all the bins one by scanning through all these bins, right? One by one, take out all the elements. As I said, these are FIFO. Don't go like a stack. Don't follow LIFO. Follow FIFO. Means this was the first element. Take it out first. The next element, take it out next. So let us follow the order. I will be emptying bins and I will write down the elements here. So let us start. This bin is empty, this bin is empty, this is 152. So write down 152. The next is 62. 62. I will separate them by comma. So these elements are gone. Next is 163. Next is 235. 146 and 36. 237, 348 and 48. $259. So I have emptied all the bins, right? And also I made them null. The elements are here. Are they sorted? No. Which is the smallest element? 36. That should come in the beginning. They are not sorted. They are not sorted. Then what? Again drop them in bins. On what basis? On the second digit from right hand side. Second digit. First we have dropped them based on this last digit. Now second last digit or second digit from right hand side. Second digit. How to take out that second digit? So for any element, what I should do is divide it by 10. So if I divide it by 10, like 152, if I divide it by 10, then I get 15. Then mod by 10. Okay, if I mod by 10, then I get 5. Yes. So divide by 10 and mod by 10. So it means earlier what we did, divide by 1 and then mod by 10. That's what we did. Now that division number has become 10 next time. Okay, we will follow this now, right? This was the first time we have done and this is the second time we will do that. So first pass is completed and this is the result of the first pass. Now we have to perform same procedure upon second digit in the second pass. So let me do it now. 152 bin 5. 62 bin 6. 163 bin 6. 235 bin 3. 146 bin 4. 36 bin 3. 237 bin 3. 348 bin 4. 48 bin 4. 259 bin 5. So I have dropped all those elements once again from array A into bins. Now empty all these bins one by one. So I will write the result here. Empty, empty, empty. 235, 36, 237. 235, 36, 237. So these are all gone. 146, 348, 48. 152 to 59. 62 and 163. So I have emptied all these bins and the elements are written here. So this is the result of the second pass. So already two passes over. Check, are the elements sorted? Smallest element is 36. That should come first. It's not there. They are not sorted. Then what? Repeat for one more pass. One more time you do it. Already two times we have done. Why third time? We did not get them sorted. Yes. Then see the digits. If you see, the largest number, that is 348, is of a 3 digit. So you have to perform 3 passes. After 3 passes, they will get sorted. Okay. Let us try it for one more pass. Now based on which digit we should do, we have finished upon rightmost digit, then the second digit also. Now we will do it on third digit. So it means first digit. From right side it is third digit. What about this? 2 digits only. Then assume this digit is 0. Okay. So for 48 also this digit is 0. 62 also this digit is 0. So now we will perform upon this one. So how to get this one? From 235, how to get it 2? See, similar. Now in the third pass, what I should do, A of I divided by 100, then mod 10. How? 2 235 if I take divided by 100, this gives what? Result 2. Then mod 10 if I do, mod 10 gives answer 2 only. So yes, divide by 100 and mod 2, then you will get a third digit from right hand side. Now based on the third digit from right side, that is third place, drop the elements in bins. So I will do it now. This is 2, so it should go into bin 2, 235, bin 2. So 235. This is 0, it should go into bin 0, that is 36. Then this is 2, 237, it should go into bin 2, 237. 146, it should go into bin 1, 146. 348, it should go to bin 3, 348. Bin 0, 48, so this is 48. Bin 1, 152, bin 1, 152. Bin 2, 259, bin 2, 259. Bin 0, 62, bin 0, 62. Bin 1, 163, bin 1, 163. All elements are completed. Now I should empty all these things. Let us start from first bin. 36, 48, 62. 36, 48, 62. Next bin 146, 152, 163. So 146, 152, 163. 146, 150, 163. So these are also gone. Next 235, 237, 259. These three elements copied there. Last one 348. So this is the end of third pass or the result of third pass. Check, are they sorted? Yes, the elements are sorted. Yes, the elements are sorted. So we have done it in 3 passes. Say it is similar to count sort, but the number of passes are more. Because we are not taking bins equal to the maximum element, we have limited bins. That's why number of passes has increased. So the time has increased. Yes, time has increased little bit. That is, the process is repeating. Same elements are being done multiple times. And that time is depend on number of digits of a number. So if you have the numbers in less than 1000, then you have to do it 3 times. Less than 10,000, you have to do it 4 times. So depending on the largest number that you have, depending on its digits, you have to do it that many times. And how to get the digits, last digit, then second last and the third last from right hand side is divide by 1 and mod 10, divided by 10 and mod 10, divide by 100 and mod 10. So this will give you the digits. So what is the time taken? We are copying all the elements and copying them back there. So it is n. But doing how many times? Depending on the number of digits. So let us say d into n. Now this d is almost like a constant. So it's not n times. So it's not n square. So we can say it is order of n. Or else say d into n, where d is the maximum number of digits. And the space is not huge. Just we have 10 bins, and the number of nodes that will be created in bins depends on the number of elements. So the space is limited and it is n. N means number of bins. So this is limited. It's not a huge space. So that's all about Radix sort. The next thing is a function. So that function I will leave it as student exercise. So you write on the function. The function will be almost same as bin sort only. Only the thing is, the copying of these elements here and again back there, this process you have to repeat for some number of times, multiple times based on this. Now this divisor was 1, continue. Divisor was 10, continue. Divisor was 100, continue. When divisor become next digit, that is 1000, it is greater than any maximum number. So stop it. So 3 times you have to run the loop, and every time this will be multiplied by 10. So when it is becoming greater than largest number, maximum number, you have to stop. So this is a student exercise. I will not explain it. You have to write on the program, and I will be showing you a demo. That's all about Radix sort. Our next topic is bucket sort or bin sort. This is similar to count sort. So let us understand this quickly because the concepts are same as count sort. Let us look at the example. I have an array of elements. This I have to sort them. Now for sorting, I need a extra memory space, so I have taken an array here. And this array size should be equal to the largest element present here, 15. So the maximum index available here is 15. This array I have to initialize it. So I will initialize them with null. So all these are null. So it means these are pointers. Pointers. Pointers to what? You will come to know. Now the setup is ready. I have an array of pointers named as bins, and the size of this array is same as the largest number present here in this array. And they are all initialized to null. Now let us start the procedure. So what is the procedure? I have to scan through these elements and copy them in these bins. Drop them in these bins or buckets. So let us start. I will scan through this array. The very first element, 6. Go to index 6 and drop that number 6 at this index. So actually I will insert that element 6 here at this index 6. So 6 is inserted here and this is null. Now this is no more null. So this is linked list. Yes, this is an array of linked list. Array of linked list. Each index, this is a bin of elements. All those bins are empty. Now this bin is having one element. So this is a linked list of elements. Yes. Next element is 8. Go to index 8 and insert element 8 at this linked list. Next element is 3. Go to index 3. Insert an element 3 at this index 3. Go to index 10. Insert an element 10. Same element we are inserting. 15. Go to index 15 and insert 15. 6. Go to index 6. Insert an element. So already element is there. So at the end, one more element will be inserted. Then 9. Go to index 9 and insert an element. 12. Go to index 12 and insert an element. 6. Go to index 6 and insert 6. So at the end of this linked list, 6 will be inserted. Then 3. Go to index 3 and insert a new element 3 here. That's all. Depending on the numbers, they are dropped in their corresponding indexed bins. 3 is dropped in bin 3, 15 is dropped in bin 15. So if you compare with the count sort, here for 2 times 3 is there, so we were writing 2, but now we have 2 nodes containing value 3s. Now one step is completed. We have copied all the elements. Now next, we have to empty all these bins from left to right and copy the elements back in array. So I'll remove these elements and show you. Yeah, I have removed the elements. Now we have to scan through these bins and empty bins. So let us scan this array of bins. First, bin 0. It's already null. It's already null. It's already null. Then what about this? Elements are there. So delete. So the first element will be deleted, right? So you have to follow FIFO-like fashion, right? Though it's a linked list. Insert at the end, delete from front. So delete 3 and insert value 3 there. Then delete next 3, insert value 3 there. Now this becomes empty. This will be empty. So when it became null, move to next. So it means until that linked list is empty, copy all the elements from this linked list in array. So likewise, I should continue all of them. I should empty all the bins. If it is not empty, delete the elements. If already empty, just move to the next bin. So I will not delete this. Let them be as it is. That is easy for us to write on the function or algorithm. But I will write down these elements, sorted elements. I'll get 6, 6, 6 3 times. Then 8 one time. Then 9 one time. The next is 10, then 12 and 15. 10, 12 and 15. So this is sorted. And assume that these are all deleted. So that's the working. Now analysis. How much time it takes? Same, n elements are copied here. Then these are n elements. They are again copied back there. So n plus n, total time is order of n. So the time complexity of this algorithm is also n. Then next, what about the space? It takes array of bins. So first of all, array is required. Then again, depending on the elements, nodes will be created. So it's taking huge space, lot of space. So if I say n is the size, that is maximum element is m, and the number of elements are n, then this is for maximum number and this is for number of elements. So this is m plus n. So this m plus n is nothing but linear only. So when it is linear, we can also say order of n. It's not that we are adding m and n is giving n. We are saying it is linear. M plus n is linear. So this is also linear. You can also say order of n. Now next I will write down the function, complete function, then I'll show you because the code is same as count sort. So here I have a function ready for bin sort. Let me explain you that function. See, the function name is bin sort. It is taking an array and number of elements. Like here the number of elements are 10. So it is taking 10. The next I have to find out the maximum number from this one so that I can create an array. So find max, this is finding an maximum number from this array n of size n. Then I should create this array of pointers of type linked list nodes. So here already I have a double pointer type bins because see, these are all pointers. So this bins is a pointer to a pointer. So I have a double pointer of type nodes for linked list. Then here I am creating an array of size max plus 1 of type node pointers. So all these are node pointers. Next I should initialize this entire array with null. So using this for loop, this array is initialized with null. Then the next thing is I should scan through this array A and whatever the element is, I should drop in that corresponding bin index. If it is 3, drop it in index 3. So scan through 0 to n, that is 0 to n. Whatever the element is, a of I, drop in that corresponding bin. That element we have to insert. So this is insert function. Insert function is for inserting an element in a linked list. And this function assume that it inserts at the end of a linked list because every element we are adding at the end. So we will write down a required function here. So it's inserting the element at the end. So this for loop is for copying all the elements from there and dropping them in the bins. Now next step is we have to empty all these bins and copy the elements back there. So for copying bins, at each bin I should go, if it is empty, then skip, empty, skip. It's not empty. So delete all the elements until it becomes empty. So this is the loop here. See, this is the loop, while loop for scanning through these bins. And at each bin until it becomes empty, we have to delete and copy the elements here. So for that, again, there is a while loop. So whatever the element is deleted is inserted in array A. So this inner loop will empty each bin. So it is similar to count sort only the difference is here we are emptying bins. That's all about the function. Now from the code, if I show you the time complexity, then this is a for loop, it taking n time. This is a for loop always take n time. But this is nested while loop, loop inside loop. So n square, no, it's not n square because what is the main operation done? Delete. So how many elements will be deleted? As many elements are there. So that are n elements only. So combined together they are taking time n only. Initialization, copying elements from A to bins and from bins to A. So total is 3n again because of including initialization. So it's order of n. So from the code also time is order of n. So that's all about the function of bin sort. Now this bin sort is taking a lot of extra space and it is having the number of bins that are equal to maximum number. Is it not possible that with less number of bins we do the same thing? That's what. Let us see the same thing with less number of bins in the next video, that is Radix Sort. It will be almost same as bin sort with some differences. So next video will be on Radix Sort. So our next topic is shell sort. This sort is useful for sorting very large size list. Name of the sort is upon a name of a person who has introduced it. This sort is an extension of insertion sort. Means it follows the idea of insertion sort only. So basically it uses insertion sort. Why insertion sort is used in shell sort? Let us understand that one. See, for explaining, I have taken an array of elements and all these elements are already sorted. If I try to sort this list of element using insertion sort, then how much time it takes? It takes just order of n time. We have already studied this. Why? It will start inserting the element from right hand side to the left hand side sorted list one by one. So it will start from this. It will try to insert 5 on this side. So this is the right place for 5 and it will stay here only. 8 it will try to insert. So 8 will be compared with 5 and 8 stays here only because 8 is greater than 5. Then 11 is compared with 8. 11 is greater, so it stays here only. Likewise, every element is compared with just one element. It will not shift any element. Every element will stay in its own place. So that's how. So total order of n comparisons are required if the list is already sorted. So this is the important feature of insertion sort, and that's why we call this insertion sort as adaptive. Now I will make one change in this one and I'll explain you something. See, I will write down 16 here and 11 here. I have just interchanged two elements. So rest of the elements seems to be sorted only because of 16 and 11 list is not sorted. Now let us see the behavior of insertion sort, how it works. It will start from here, insert 5, so 5 remains there only. 8, that is greater than 5, so it will remain here only. 16 greater than 8, so remain here only. 13 is smaller, so 13 is shifted here. So 16 comes here, 13 goes there. Then again 13 is compared with this one. So this is greater, 13 is greater, stay there only. Then coming to the next element, 11. 11 is smaller than this one, so 16 comes here, 11 goes there. And 11 is still smaller than this one, so 11 comes here and 13 goes there. Then 11 compared with 8, nothing will happen. 18, now last element, 18 is compared with 16, nothing will happen, no shifting. So just with few elements are shifted and the elements are sorted. So if the array is not sorted due to few elements, then it will take very less time in insertion sort to arrange them in proper places. It requires very few shifting of elements. This is the idea used by shell sort. So let us understand how shell sort works. So for explaining shell sort, I have taken an example, a list of elements. There are 11 elements in this array. Now let us see how shell sort works. Like in insertion sort, the elements are inserted one after another consecutively, that neighboring elements are inserted. But in shell sort, the elements are inserted, but they are distance apart. So there is a gap in between the elements. So let us see what is gap. See, gap is defined with number of elements by 2, and we will take a floor value. Here the number of elements are 11. So gap is 11 by 2. Floor value gives 5. So initially gap is 5. So we will sort the elements, not the consecutive elements, but the elements with a gap of 5 or distance of 5. How? I will show you. At this gap, we will again divide it by 2. Again we perform the insertion sort with that gap. So we will go on reducing the gap until gap becomes 1. So let us see what is it. So let us see how we perform insertion sort in between the elements with a gap of 5. So let me perform this one. See, initial element is this one. First element is this one. Now, which is the element with a gap 5? 1, 2, 3, 4, 5. So just let us take these two elements, nothing else. So assume that there are only two elements in a list. As per insertion sort, we assume that the first element is sorted. So we have to insert this element on the left hand side. So compare this one. We are inserting 6 now. 6 is smaller than 9. So shift 9 here and bring 6 here. 6 is brought here and 9 is here. Now if you look at just these two elements, don't see anything else, only 6 and 9, they are sorted. First is 6, then next is 9. Now this is the basic step, and the same step we will continue. Now I will slide this one. So this will point on 1 and this will point on 1, 2, 3, 4, 5 with a gap 5. So this is on 6. Now we consider these two elements. This 5 is sorted. Then insert 12. 12 is greater than 5, so it remains here only. So they are perfect. So they are already sorted. Just two elements. Now let us slide to the next location. So 1, 2, 3, 4, 5. Anyway, this is also moving to the next element. So we don't have to count every time. This is moving, so this is also moving. Compare these two. This is already sorted, 16. So 10 we will insert it. So 10 is smaller. 10 comes here, 16 goes there. Then again slide. So this one with this one. 8 is sorted. 4 we are inserting. So 4 is small. So 4 comes here, 8 goes there. 8 is here. Then again slide this. Move to the next element. This is again 5 elements away. 1, 2, 3, 4, 5. Compare these two. 13 and insert 2. 2 is smaller than 13. 2 comes here. Then 13 moves here. So 2 and 13 are swapped. Now before moving to the next element, I want to show you one thing. See right now, from 13 if you see, from this side, 1, 2, 3, 4, 5. Yes, the gap is 5. From 2 you check the gap this side. 1, 2, 3, 4. So there is no element at position 5. Array ends at 4 only. Right? Array ends at 4 only. So for all the elements which I have moved just now, for them the array was ending here. Right? Now I will move to the next element. This one. 1, 2, 3, 4, 5. This one. Compare these two. 9 is sorted. 3 we are inserting. So 3 is smaller. So 3 comes here and 9 goes there. 3 comes here, 9 goes here. Then from here if you start 1, 2, 3, 4, 5. From here if you start 1, 2, 3, 4, 5. Oh, this is coming as a fifth element. See, this should also be included. Right? See, with a gap of 5, we have 3 elements, not just 2 elements. 3 elements are there. So actually, we should insert 3 by comparing these 3 elements. See, 3 was here, so it came here. So I should include all 3 elements. So consider 3 elements as one list. So from here, I brought 3 here. Then still compare with this one. So 3 is still smaller than this. So 3 comes at this place and 6 goes here. So that's all. The last index, we have reached the end of the array, end of a list, so stop. We have tried to perform insertion sort between 2 or 3 elements as a list with a gap of 5. So what we have done in this one is just we have scanned through the list once. Few swappings are done, not many swaps, right? Few swappings are done, few shiftings. So that's what the idea of shell sort is. If you try to shuffle few elements, then they may get quickly sorted. So we have seen first pass. This is first pass with a gap of 5. Now gap is 5. Again perform division by 2. 5 by 2 floor value. This is 2.5, so this is 2. Now again we have to do this with a gap of 2. Now with a gap of 2 in a list, the number of elements will be more. So now I will start with a gap of 2. This is the first element. Then 1, 2. This is the next element. Then 1, 2. So this is the next element. 1, 2. This is the next element. 1, 2. So this is the element. 1, 2. So many elements are there. So we have to perform insertion sort upon these elements. 3, 10, 2, 12, 8 and 9. We have to perform insertion sort on those set of elements. Now the number of elements in a list has increased. But we will be doing upon only 2 elements at a time. Let me show you how we can proceed. I'll remove these marks. Let us start. First element is this one. 1, 2. This is the next element. Now compare 3 with 10. So 10 is greater than 3. So it is in the right place. So this is sorted. Then move to next element. 5, then 1, 2, so this is on 4. Now 4 with 5, 4 is smaller than 3, so bring 4 here, send 5 there. Then from here try to move back 2 elements, 1, 2, no, we are going out of list, don't do anything. Continue, move to the next element. So this comes on index 2 and this moves on to index 4. 2 with 10, so 2 is smaller, so 2 comes here, 10 goes there. Then again from here, see from here if you see 1, 2, then from here 1, 2, yes, this is also included. So compare 2 with 3, so 2 is smaller, so write 2 here and send 3 there. So that's it. So we have to insert the element with those elements with a gap of 2 as long as it is adjusted. So we have now more number of elements because the gap is less. Let us continue. We are here. So next we will move on to this and we will move to this one. Now compare 6 with 5. So 5 is smaller, 6 is greater, so we don't have to shift. Then move to next. This one. Now 12 is greater than 10. So 12 is greater, it is in its own position. Then move to next. 6 and 16. So 16 is greater than 6. It is in its proper position. Move to next. Now 12 and 8. 8 is smaller than 12. So bring 8 here and send 12 there. Now this element should be compared again with the second element this side. So 1, 2, compare with this one also. So 10 and 8. So 8 is smaller than 10. So bring 8 here, send 10 there. Then again compare this with 2 elements. So this one. So 8 is greater than 3. So 3 is smaller than 8. We don't have to shift. So once you get a smaller element, we can stop. We don't have to go further. So here, we were here. Now move to next element. This is on 16. And the next element here, it is on 13. That is index 9. 13 is smaller than 16. So shift here. 13 comes here and 16 goes there. Then as it has shifted, again check with the second element in this backward direction. So this one. So 13 is greater than 6. So 6 is smaller. So stop. Once we got a smaller element, stop. Then I will remove this. We were basically here and this was the second element. Now next is this one with this one. 12 and 9. 9 is smaller. So shift 9 here, send 12 there. As it is shifted, then again compare with the second element this side. So 10 and 9. So 9 is smaller than 10. 10 is greater. So bring 9 here, send 10 there. Then as it is shifted, again compare with the second element this side. So this is 8, but this is 9. So 8 is smaller than 9. So we don't have to continue checking. It is sorted. So as this is the last element, I will show you all second elements. See 1, 2 and 1, 2. So if you check this 2, 3, then 8, then 9, then 10, then 12. So 2, 3, 8, 9, 10, 12, these elements are sorted. Yes, it's forming a single list with gap of 2, 2. So we have finished second pass. It was little lengthy because the number of elements were more. So that's all. This is the end of second pass. So we have finished second pass. So when we have finished, when the marker reached here, so this we can take it as a primary one, right? This is the primary marker. So first element was this one and second element was this one. So actually this is the one we have to track. And once it reaches this end, we should stop, right? So now we will perform one more pass by reducing the gap. So what is gap now? Gap is 2. So gap is 2 means this is 2 by 2 and this is 1. So now finally this is going to be a last pass because gap has become 1. So first time gap was 5, the next gap was 2, now next gap is 1. So we have to sort it with one element gap. So I'll remove these marks. Now I'm going to perform this insertion sort with a gap of 1. As the idea of shell sort is, as we have performed with a greater gap, already the elements are adjusted. Most of the elements are adjusted. Now the remaining work is very little. Very few elements will be shifting. Let us see. Now in this pass, as the gap is 1, so it will be same as insertion sort. So this is the first element, this is the second element. So I will not take two marks, I will just take one mark. We are going to insert this one now, right? On which side? Left hand side. 4 is greater than 2, 2 is smaller, so it is sorted, leave it. Then 3, if you compare, 4 is greater than 3, so interchange. So 3 comes here, 4 goes there. See, there was one shifting, right? Now continue. 5, compare with the previous element with a gap of 1. So 5 is greater than 4, so 4 is smaller, no need to shift. 8 is greater than 5, no need to shift. 6 is smaller than 8, so okay, shifted. So 6 comes here, 8 goes here. Then continue from this place, so stop. So you don't have to shift it further. Then this was our actual mark. Move to the next element. 9 is greater than 8, so we don't have to shift. 13 is greater than 9, so we don't have to shift. 10 compare with the previous element. So 13 is greater, 10 is smaller. So bring 10 here, send 13 there. Then still compare with the previous element. So 10 is bigger than 9. 9 is smaller. You don't have to shift with 9. Now move to next. 16. Try to insert 16. 16 is greater than 13. No need to shift. 12 is smaller than 16. Yes, it has to be shifted. 12 here, 16 here. Then still continue with the previous element. 12 is smaller than 13 also. So 12 comes here and 13 goes there. Then still compare with the previous element with one element gap. So 12 is greater than 10. 10 is smaller. So until it gets adjusted, go on shifting it. So very few shiftings we have done if you observe. No element was brought till here, right? If any element was getting shifted, one or two places it was getting shifted. So because we have already done few shiftings in the beginning, so that has reduced large number of shiftings in last pass with the gap 1. That's all. This is shell sort. We got the element sorted. This was the last pass. See, for this sort, definitely you have to work on it. Take the same example and you do it by yourself. Then you can remember it. The other sorts, if you have watched them without working also, it's easy to remember. But this sort, you have to work on it. Now we'll do analysis of shell sort. See what we are doing in a pass. We are scanning through elements and limited shifting. Few elements we are shifting, right? Just few elements we have shifted. That is negligible. So we can just focus on scanning of elements. So how many elements are there? N elements we have scanned. That's all. So in each pass we have scanned N elements. Then how many passes we have performed? See, for 11 elements we have performed 1, 2, 3 passes, just 3 passes. How we were getting these passes? How we decided we have to perform only 3 passes? Number of elements was divided by 2, result was again divided by 2, result was again divided by 2. When we reach 1 we have stopped. So this was nothing but successive division by 2. So successive division is nothing but log. So that log we have applied on n. So this is log n base 2. So in each pass we have performed scanning of all n elements and log n passes we have performed. So this is scan a list and this is number of passes. So this is analyzed as n log n. So this is the time complexity. Now more on this one, more about analysis. As I said that shell sort is useful for sorting very large size list. And the gaps I have taken by dividing them by 2. Sometimes gaps are taken as primary numbers. So here the number of elements are 11. So smaller than that 11, the prime number is 7. So we can have a gap of 7, then have a gap of 5, then 3, then 2. And finally we can perform for 1. This is also possible. So you can select the gap as a prime number also, or you can select the gap by dividing it by 2. So there are variations possible in this one. So it's also sometimes analyzed as order of n power 3 by 2. So this will be less than n square, that is n power 1.5. And also it is analyzed as n power 5 by 3. So this will be n power 1.66. So either you can say n log n, or you can say n power 1.5, or also you can say n power 1.6. So analytical results are various. So the way I have explained you, from there you can clearly see that it is n log n. So I have not considered shifting of elements. And few more things about shell sort. See, shell sort is following insertion sort. So insertion sort is adaptive. So shell sort is also adaptive. The next point is shell sort doesn't take any extra space. So it is in place sorting. Within the same array, we can sort the elements. And it comes under comparison based sorting. Under comparison based sortings, if you remember, there was only one sort, that was merge sort, which was using extra space. Otherwise, all the sorts are in place sort. So shell sort also comes under in place sorting. So that's all about the analysis. I will write on a function for shell sort and I will discuss that. In this video, I'll write a function for shell sort. Already we have seen an algorithm for shell sort and we have discussed about it. So it's a simple function. It will be following the method of insertion sort. So let us write on a function for shell sort here. It takes array of elements and the number of elements. Now inside this I need few variables, so I will declare them like a gap variable, and I and j. Then the first for loop is gap that is started by n by 2 and gap is greater than 1, and then gap is divided by 2 every time. So this is the outermost loop. Then inside that for I that starts from gap and I is less than n and I plus plus. Then inside this we need a temporary variable, in that we will have an element of a of I that we want to insert. Then j should start from gap minus I. Then a loop that is for shifting all the elements. So while j is greater than 0 and a of j is greater than temp, and every time a of j plus 1, we will copy a of j and j minus minus. Then at a of j plus gap, we will assign the element from a of j, and j should decrement by j minus gap. Then after the end of this loop, we should copy the element temp at j plus gap. We should copy the element temp. I minus gap, this is I minus gap. Then now this array is same. Already I have used this in many programs, so I will call shell sort here by passing array of elements and the number of elements. Let us see the result. The result is 3, 5, 7, 9, 10, 11, 12, 13, 16 and 24. Yes, perfect. This is working perfectly. So that's it. So you can write on this program and try it by yourself. And also we have Radix Sort and bin sort that you are supposed to implement it. You write on the code for it. That's all in this video.